So, good evening, everyone, and a very warm welcome to all our guests, dignitaries, speakers, faculty members, and all our participants for joining us today from across the country and abroad for the Golden Jubilee Lectures on Voyage through the Cosmos, History, Models, Theories, Latest Images, and Foundational Issues in Understanding the Universe. My name is Dr. Roshan Tiwari, and it is my great privilege to be your host for today's event. The lecture series begins today on the 16th of March, Monday, and will continue till the 22nd of March, Sunday, in online mode, bringing together distinguished scientists, scholars, and brilliant thinkers around the world. The timings of the lectures will be 5 p.m. to 8 p.m. from Monday to Friday, and 10 a.m. to 1 p.m. on Saturday and Sunday in Indian Standard Time. This lecture series is organized by Bhaktivedanta Institute, Kolkata, as a part of its Golden Jubilee celebrations, marking 50 years of dedicated service to humanity. We would like to acknowledge our knowledge partners, including Jigyasa Science Consciousness Inner Quest Group, IIT Bhubaneswar, Uttarakhand State Council for Science and Technology, Dehradun, Soya University, Bhubaneswar, Techno India University, West Bengal, Government PG College, Ranikhet. We sincerely thanks many renowned institutes and universities across the world, across the country, for all their support in organizing the event. So now, to begin this program on an auspicious note, I would like to invite Vrajlika Devi, Sulochana Devi, and Prema Vinodini Devi to kindly offer the invocation. Please. Invocation team, please on your video. Invocation team. Yeah. We can start. Yeah, you are muted.
Vindam Adipurusham Tamaham Bhajami Govindam Adipurusham Tamaham Bhajami Govindam Adipurusham Tamaham Bhajami Venam Kvanam Tam Aravinda Dalayataksham Varahavatam Samasritam Buddha Sundarangam Kandarpakoti Kamaniya Visheshashobha Govindam Adipurusham Tamaham Bhajami Govindam Adipurusham Tamaham Bhajami Govindam Adipurusham Tamaham Bhajami Anganiyasya Sakalin Driyavrittimanti Pasyanti Panti Kalyanti Chiram Jaganti Ananta Chinmaya Sadhu Jala Vigrahasya Govindam Adipurusham Tamaham Bhajami Govindam Adipurusham Tamaham Bhajami Govindam Adipurusham Tamaham Bhajami Govindam Adipurusham Tamaham Bhajami Govindam Adipurusham तमहं भजामि गोविन्दम् आदिपुरुषं तमहं भजामि.
Yeah, thank you. Thank you very much for that beautiful invocation. So before we proceed further, I would like to share a very interesting short introductory video about the lecture series. Please have a look.
The universe is marvelous. Just look at the sky. Huge planets, bright stars, vast galaxies, massive clusters. It just fills us with tremendous amazement. In the last century, our exploration of the cosmos has reached unprecedented depths. From the first echoes of the Big Bang to the accelerating expansion of space, from dark matter and dark energy to ripples in space-time itself. Yet, with every answer, deeper questions have arisen. How far are we in understanding our universe? What lies at its beginning? Are there limits to knowledge, observation, and even comprehension? Is the astonishing order of the cosmos merely accidental? Or does its beauty, fine-tuning, and mathematical elegance point toward a deeper intelligence and purpose, as some of the greatest scientific minds have reflected across generations? To explore these profound questions, Bhaktivedanta Institute invites you to an extraordinary voyage through our cosmos, where some of the world's most brilliant scientific minds will share their insights and discoveries, including Andre D. Linde from Stanford University, John H. Schwartz, theoretical physicist, Caltech, USA, Wendy L. Freedman from the University of Chicago, Ofer Lahav from University College London, Avi Loeb, Harvard University, USA, Pankaj S. Joshi International Center for Space and Cosmology, India, and many more leading thinkers from across the globe. This is a space for rigorous science, open inquiry, and meaningful dialogue, where curiosity meets humility. Welcome back to your own astonishing home, the universe.
So it was a quite interesting video. So it is now my great honor and privilege to invite Sri Vasudev Raoji, President of Bhaktivedanta Institute, to deliver the welcome address. So before this, I will just give a brief introduction of him. So Sri Vasudev Rao obtained his MTech in Computer Science 1998 from IIT Kanpur, India. After a brief tenure of working as a software professional, he decided to significantly contribute for the cause of humanity. Under the able leadership and vision of Dr. T.D. Singh, the founder director of Bhaktivedanta Institute. Since past 25 years, he has been instrumental in actively fostering dialogue on foundational questions in science. His deep interest in the foundations of mathematics, computer science, and logic, and their implications for understanding reality, has brought him into conversation with renowned scholars worldwide. So with this, sir, I would like to invite Sir, please.
Thank you, Dr. Roshan. And good afternoon and good morning, those who are in different time zones. Respected dignitaries of the inaugural session. Our chief guest, Dr. A.K. Anil Kumar, Director, ISRO Telemetry Tracking and Command Network, ISTRAC India. And our guest of honor, Professor Annapurni Subramaniam, Director, Indian Institute of Astrophysics, Bengaluru, India. And our another guest of honor, Professor Dipankar Banerjee, Vice-Chancellor, Indian Institute of Space Science and Technology, Thiruvananthapuram. And our program chair, Professor Manoranjan Sinha, Department of Aerospace Engineering, Indian Institute of Technology, Kharagpur. And the delegates who joined this voyage through the conference, Cosmos, who are scientists, teachers, and professional students. I would like to welcome you to the Voyage to the Cosmos, exploring the history, models, theories, latest images, and fundamental issues in understanding the universe. Among the great mysteries that make humans curious about, the cosmos stands out the greatest and universal. From early ages of the mankind to the modern scientific age, cosmos has nurtured, guided, and intrigued all human life. Even a toddler who is unable to ask any questions wonders about the twinkling stars and the shining moon. Such is the mystery of our observable universe that it had deep impact on our curiosity, from which the science itself was born. The beauty in the visible universe and the beauty of the equations that describe it both intrigue the deep thinkers. What is the origin of the universe and its laws? Is beauty a fundamental aspect of the universe? Are there a greater meaning and purpose of the universe and our existence? From studying the visible patterns of the cosmos and using them to mark the seasons and times of the day, we have come a long way in probing and predicting the universe beyond the visibility of the naked eye. Thanks to the incredible advancements of science, our observation range was expanded by carefully crafted optical telescopes. The range of observation was further expanded by radio telescopes. We have even changed the point of observation from the Earth into the cosmos itself by launching the telescopes into space. We could confirm the space-time curvature of the universe by predicting and observing cosmic events. The detection of cosmic microwave background was useful to predict the beginnings of the universe. The James Webb Space Telescope, launched in 2021, has revolutionized infrared astronomy by capturing detailed images of early galaxies, star formation, and exoplanet atmospheres, some of the most distinct objects ever observed. An exoplanet is a planet that orbits a star outside our solar system. Since the first confirmed discovery in 1992, over 6,000 exoplanets have been confirmed, spread across more than 4,500 planetary systems. These worlds exhibit extraordinary diversity, including hot Jupiters, super Earths, mini Neptunes, and Hysian worlds, planets with ocean-covered surfaces and hydrogen-rich atmospheres that may support life beyond traditional habitable zones. The search continues for Earth-sized planets in the habitable zone of Sun-like stars, with estimates suggesting 11 billion potentially habitable Earth-sized planets may exist in the Milky Way alone. With uncertain conditions on the Earth, our survival seems to depend on our cosmic success. Cosmology is one of the important research areas of the Bhaktivedanta Institute. On the occasion of the Golden Jubilee celebrations of the Bhaktivedanta Institute, we are happy to welcome you to this Golden Jubilee Lecture Series on the voyage through the cosmos, with inspiration from Albert Einstein, who exclaimed, "The most beautiful emotion we can experience is mystical. It is the power of all true art and science. He to whom this emotion is a stranger, who can no longer wander and stand wrapped in awe, is as good as dead." To know that what is impenetrable to us really exists, manifesting itself as the highest wisdom and the most radiant beauty, which our dull faculties can comprehend only in their most primitive forms. This knowledge, this feeling, is at the center of true religiousness. In this sense and in this sense only, I belong to the rank of devotedly religious man. Let me express few words about the Bhaktivedanta Institute, the organizer of this event. Bhaktivedanta Institute was founded in 1974 by scientist Saint Dr. T.D. Singh, who obtained his PhD in physical organic chemistry from the University of California, Irvine, and Srila A.C. Bhaktivedanta Swami Prabhupada, a visionary saint for the modern age. The emblem of the institute mentions a verse from Vedanta, Athato Brahma Jignasa, inquire into the absolute. The institute thus promotes inquiry or curiosity into the meaning and purpose of life and the universe we live in. It thus focuses on foundational questions of life and universe, such as what is life, what is consciousness, why are we here, why this cosmos. It believes that in search for the answers to these questions, a multidisciplinary approach is necessary, where ancient wisdom and traditions will be partners. For example, Indian traditional knowledge systems have incredible information about the universe. The age of the universe that is comprehensible, that is comparable to the scientific age of the universe, the structure of reality indicating multiverse, the relativity of time, extraterrestrial life, etc., to name a few. Bhaktivedanta Institute is celebrating 50 years of Golden Jubilee these years, 2024 to 2026. As part of these celebrations, various events are being organized, starting from a lecture by Nobel laureate in physics, William Phillips, in January 2024, and then summer schools on origin of information and quantum foundations, and then a special conference on consciousness and various other events. By the blessings and vision of its founder, Dr. T.D. Singh, also known as the scientist saint, Bhakti Swarup Damodar Swami, despite various challenges and difficulties, the institute is continuing its humble activities from past 50 years to help humanity through interface of modern scientific temper with ancient spiritual wisdom. I welcome you all, the distinguished dignitaries of the inaugural function, speakers, guests, teachers, professors, professionals, and students to this online voyage through the cosmos. Thank you for joining us.
Yeah, thank you very much, sir, for your inspiring welcome address and giving us an account of recent events by Bhaktivedanta Institute. So now we are truly delighted to have among us Professor Manoranjan Sinha from Department of Aerospace Engineering at IIT Kharagpur and Program Chair of the Voyage through the Cosmos Lecture Series. Professor Sinha is a distinguished aerospace scientist whose research spans space flight mechanics, satellite attitude dynamics, and advanced aircraft control systems. His pioneering work on Lorentz force-based satellite attitude control addressed a 6-decade-old challenge in satellite dynamics. He is also a passionate educator, having taught a wide range of subjects from flight mechanics and spacecraft dynamics to neural networks, mentoring generation of students in aerospace sciences. So now I would like to humbly invite Professor Manoranjan Sinha, sir, to kindly give us an overview of the exciting program. Sir, please.
Thank you, Dr. Tiwari. Okay, so I welcome everybody. So I'll start formally, like distinguished speakers, respected colleagues, dear students, and honored guests. Welcome to all of you. It is a great pleasure and privilege to welcome all of you to this lecture series titled Voyage Through the Cosmos: History, Model, Theories, and Foundational Issues in Exploring the Universe. So cosmology, perhaps it is the only subject where only few instruments are used, and using sophisticated or complicated mathematics, we try to understand the universe and its origin and what will be its fate. But the most surprising thing about the universe is, or either you say about the cosmology, is that the moment we get one question answered, so many other questions start coming to us. Okay, so as a human being, we have been trying to understand this universe from long time. The present series of the lecture by renowned and eminent cosmologists of the world, this is an humble attempt to explore our existence in terms of the language of the science that we understand today. So what we get in the some of the earlier texts, so there the language is different. What we understand today, this language is different. So our effort is at this time to understand the language what we are tackling today and or what we know today. So sometimes we miss to remember that our life and size are extremely insignificant on the cosmic scale. And because of this, we miss to develop humility, and this leads to many social conflicts. So at an advanced stage, all these things become eliminated. And as stated in Bhagavad Gita, it is one of the ancient spiritual texts of India. Brahma Bhuta Prasannatma na sochati na kanchati sama sarveshu bhutesu madbhakti lapte param. So one who is transcendently situated becomes joyful in the self. Such a person neither laments nor desires anything. Being equal toward all living beings, he then attains supreme devotion unto me. So what I want to state here that the current effort of the cosmology, the earlier effort, okay, and what the knowledge is exists in the spiritual text. So broadly, we can divide it into three parts. So one is the Surya Siddhanta model and its equivalent, which is basically geocentric model. So this is based on direct perception. Okay, very few like some optical instruments were used, and using this, then the people tried to understand what this planetary system is and what the universe is. So, in the modern cosmology, we have been using sophisticated telescope, radio telescope, optical telescope, satellite-based telescopes. So, and based on this, then we gather the knowledge. So, this is basically method of inference, what we call as the inductive knowledge. Okay, and the Vedic model of the universe, which is given in some of the spiritual texts of India, this is based on revealed knowledge. This is called the deductive knowledge, okay, or what we call as the top down approach of gaining the knowledge. So if you see our revolutionary transformation, this started with the general theory of relativity, okay, so which was proposed by our great Albert Einstein, and this provided a new framework for understanding the gravity, okay. And from there onward, then soon after this, Edwin Hubble, he revealed that distant galaxies are moving away from us. So from that, he concluded that universe must be expanding. So this discovery then led to the development of the Big Bang theory, okay, which describes the universe evolving from a hot, dense initial state approximately 13.8 billion years ago. But interestingly, in the Vedic text, the universe age is given to be more than 155 trillion years. This is trillion years. Okay, so it is much bigger than what we see this 13.8 billion years is. Okay. So this difference may be because we judge our universe based on our observation, so which is basically the observable universe. So, but this universe, whatever we are observing, so primarily this is based on inductive knowledge, or we are inferring the knowledge from our observation, like the presence of the dark matter or the dark energy. So how do we refer to infer this? Because of anomalous rotation of the galaxies, they are rotating uh, much faster. So and from there, then I will not go into the details. Then it's a infer that there must be some other matter which is being called as the dark matter, okay, present for must be present, which is responsible for maintaining the structure of the galaxy. So this is basically again, you see, this is an inductive approach, or we are doing certain inference based on certain observations. However, this discoveries raised deep foundational question: what is the true nature of the space-time? Okay, whatever till today we have got all those knowledge, but still it's not complete, and we have many questions. So, what is the true nature of the space-time? What do the fundamental constants of the nature have? The why do the fundamental constants of the nature have the values they do? Okay, what is the origin of the cosmic structure? And perhaps the most interesting or the most sacred part, what happened at the very beginning of the universe? So this is not known to us, all these things. So now you see that the proper time along a photon path, this is zero. This is called the null path. Okay. And the phenomenon of the quantum entanglement, you must be knowing it. Now it's a well known to most of the students and even the scientist community from different streams. So they imply that the space-time, they even may imply, okay, that the space-time is not fundamental, rather they are the emergent property of the quantum activity. So beside this, we have many other concepts floating around, like the multiverse hypothesis. Interestingly, the multiverse hypothesis, it's already present in the Vedic text. I will show you in my lecture once I toward the end of this series. So in my lecture, you will see all these things happening there. The multi-inverse uniform information is present there. Then we have many radical ideas right now, like the Brann's steady state holography, plasma field, or the Big Bang universe, okay, superfluid space-time simulation theory, or the anthropic principle of cosmology. There are so many of them. Okay, but out of that, Big Bang is having the measure is, and it's widely accepted. But others are also there, and they are being proposed. Some of new things are coming up to understand how the universe is working. If we face one problem, we propose something new. So this is because this is inductive knowledge. Inductive knowledge will be always like that. We will be inferring. So as we get more information, so then we infer further. So this will grow over a period of time. So this title, I would like to point out one more thing, like the Stephen Weinberg, he was a well-known cosmologist. So he has stated, it is there in his book, it's written, the physics is not a finished logical system, rather at any moment it spans great confusion of ideas. Some that survive like the folk epic from the heroic periods of the past, and the others that arise like utopian novels from our dim premonitions of a future grand synthesis. And this seems to be correct, because this is implicitly implying that our understanding of the universe is in nascent stage, and we need to go very long before we appreciate it better. So the present title, The Voyage Through the Cosmos, is therefore particularly appropriate at this instant, and our journey is far from complete. So each generation of scientists, they are pushing the boundary of knowledge a little further, often discovering the universe is even more surprising than we have imagined. So I hope that these lectures will not only deepen our understanding of the cosmos, but also stimulate new ideas, new collaborations, and perhaps even new paradigms of exploring the universe, and also inculcate humility and produce a spark of understanding the meaning of the life. So we have many stalwarts who will be taking us through the secrets of the universe. On the very first day today, we have Professor Wendy Freedman. She will be telling us about something missing in our understanding of the universe. Then we have Professor Loeb, who will be letting us know about the current status of discovery in the extraterrestrial object search. On day 2, we have lecture by Professor Professor Paul, then who will be talking about the fallacy of the Big Bang model. Okay, so this may be interesting to all of us. Then Professor Andre Linde, he will also be speaking tomorrow. On day 3, we have Professor Ofer Lahab and Professor Tim Eastman and Professor George Ellis. They will be delivering lectures. On day 4, we have Professor Louis Marmot and Professor Mario Levy and Professor Tejinder Singh. Day 5, we will have lecture by Professor Luke Barnes, Professor Frank J. Tipler, and Sri Vasudev Rai. And day 6, Professor John Searle from the Caltech, he will be delivering the lecture, and also David Dilforth and Sri Varun Agarwal will be delivering lecture. On the 7th day, I myself will be delivering lecture along with Professor R.N. Iyengar and Professor M.S. Sriram. Okay, so with these thoughts, I warmly welcome all the speakers and participants. I look forward to the stimulating lectures and discussion that will follow over the course of this program. Thank you, and I wish that this lecture series proves to be a very successful and intellectually rewarding voice through the cosmos. Thank you very much.
Yeah, thank you. Thank you very much, Professor Sinha, for giving us such a wonderful overview of the lecture series and also highlighting some of the foundational questions in cosmology. So now we are deeply honored to have with us our distinguished guest of honor, Professor Dipankar Banerjee, Vice-Chancellor of IIST Thiruvananthapuram. He is an eminent astrophysicist and a leading expert in solar physics. He has made significant contributions to our understanding of the sun and its impact on space weather. He served as a director of Aryabhat Research Institute of Observational Sciences, Aries, Nainital, and was also a senior professor at Indian Institute of Astrophysics, Bangalore. He is the co-chair of the Science Working Group of the Aditya Mission, which is the first dedicated Indian mission to study the sun, launched by ISRO. Through his work in research, academic leadership, and international collaborations, he has inspired many young scientists in the field of space science. So please join me in welcoming Professor Dipankar Banerjee as our honored guest of today. So please, sir, welcome.
Thank you very much for this opportunity. I think it's very heartening to see a large number of students enrolled for this program. And I see that, you have a really eminent scientist from the globe, who will be lecturing in this, next week or so. So I am a poor astrophysicist in terms of I only look at the closest object, which is the sun. But hopefully I'll be able to, take you through this journey to understand our sun through different space missions. So I think my lecture is scheduled on next Sunday, and I will try to give you an overview about the mysteries of our understanding of the heliosphere in general. So sun and the planetary systems and beyond, we call it as a heliosphere. And as you understand that our presence here today is because of the presence of the sun at an appropriate distance away from us. So our life and existence is primarily because of the solar radiation. But then a sun, apart from its radiation, it also, throws away a lot of particles, along with sometimes, huge magnetic field. So that do affect our near Earth environment also. So this is a field called space weather. And as you know, our near Earth is filled with lots of satellites, and these satellites directly gets impacted by material which is coming from the sun. So it is very important for us to understand the solar variability in terms of its short term, like, when these huge explosions happens in the sun, we call it flares or coronal mass ejections, how it affects the near Earth environment and how we can protect the space assets, including now humans in space. So that's some subject area of really our regular concern now. And as you can also see with the advancement of space defense, how important it is to understand the space, because all our space surveillance assets are also getting influenced by solar variability. So I will take you through that journey next Sunday. But I am actually really, really quite impressed with the variety of subject areas which is going to be covered during these 2 weeks of almost 10 days program by a very eminent scientist. So that will take you a voyage through the cosmos and the mysteries of the universe. Our existence is all questioned. Why are we unique in the universe? So all these questions, our curiosities, you'll be able to get some insight through these classes. So all the best for these program. Just on an institutional basis, I must point out that right now I am in Trivandrum. This is an institute called Indian Institute of Space Science and Technology. We work very closely with the Indian Space Research Organization, and also more recently the space domain has been privatized. So there are many more startup companies who are interested into the space domain. So as a academic institution, we are working very closely with all these new space players. There are lots of very young enthusiast startups which has come up in last couple of years. So we are also looking forward to work with them. And our graduates, postgraduates, and PhD students are part of this system. We have about 1,500 scientists and engineers working in different projects in ISRO itself. And there are many who are actually started up their own startup companies, in India as well. So some of you may get some sort of, ideas, or if you have some questions about how to join in Institute of Space Science and Technology and what are the prospects of Indian space, ecosystem, I'll be happy to answer those also. So you can start preparing your questions for next Sunday during the lunchtime. Thank you, and I'm looking forward to this very exciting program. Thank you very much.
Yeah, thank you. Thank you very much, sir, for your inspiring and quite enthusiastic words. I think it has created a curiosity in minds of our students and participants. So thank you, sir. So we are also deeply honored to have with us another distinguished guest of honor, Professor Annapurni Subramaniam, Director of the Indian Institute of Astrophysics, Bangalore. So Professor Annapurni Subramaniam is a renowned astrophysicist whose research has significantly advanced our understanding of star clusters, stellar populations, evolution of galaxies, and ultraviolet astronomy. She has contributed to the 30-meter telescope TMT, which is being built by an international consortium with India as a partner. So she is the principal investigator of the proposed next generation UV optical space telescope also. So through her dedication to science and mentorship, she continues to inspire the next generation of astronomers. So please join me in extending a warm welcome to Professor Annapurni Subramaniam. Ma'am, please.
Yeah, hello. Can you hear me?
Yes, ma'am.
Yeah. So good afternoon, everyone. So I'm happy to be here, and very nice to see a large number of lectures which are going to be coming in the next few days. Very exciting topics from very well-known, renowned people, internationally renowned people from all over the place. So I think it's a very wonderful opportunity for the students and who are all participating in this particular event to understand it gives you an overall picture of where we stand with respect to current knowledge in astrophysics, and that is from the experts themselves. So it's very, very unique from that point of view. I think I congratulate the organization for bringing all these people together in one umbrella, and bringing so many different talks on wide variety of topics as well. So just to talk about what the Indian Institute of Astrophysics has contributed to the ecosystem of astronomy and astrophysics in the country. Can I share a couple of slides on that, because then I can speak on based on that particular thing.
Sure, ma'am. Sure.
Shall I?
Sure.
Yeah, I just have a couple of slides to show that this is one comprehensive slide on what the Indian Institute of Astrophysics has been doing. I must also say that Dipankar and I've been colleagues for a very, very long time, and contributed to the activities of the Institute for a very long time as well. So Indian Institute of Astrophysics has been exploring the universe since 1786. So it's a very, very long time, and it was under the name called Madras Observatory, and a lot of activities have been carried out between 1786 to 1899. And that includes the discovery of helium from India in a total solar eclipse happened in 1868. And the measurements were taken from Machilipatnam and Guntur. And if you, that is the first, that's only one element which is actually observed in the sun and not on the terrestrial earth. And that's why it has the name helio, to do with the sun. So that was one of the main contributions. There were also other contributions such as, if historically, if you see the Indian astronomy as such, we had techniques to estimate latitudes, but there were a lot of difficulty to estimate longitudes, because the reference was sometime Ujjain, and then the reference became Greenwich. And when you have large distances to cover and times to be, longitude is basically difference in time, right? So if you look at it, it's been very difficult, but one uses events such as, the eclipses, or even the eclipses of the moons of Jupiter itself to measure that. So one of the frontline measurements were done in Madras Observatory in 1800s. The then director of the observatory actually made measurements and established the longitude, and that was important not only to astronomy, but also to many things, even navigation, and also for our great trigonometric survey, which also was happening over there. So identification of longitude was important. That also was contributed. Later on, they decided to move the observatory from Madras to a better place to study the sun better, because they started knowing more about the sun and wanted to understand how the energy is created, how the what is the chemistry happening over there, etc. So they decided to move it to a stable place, which was identified as Kodaikanal. And Kodaikanal, it came in 1899, and ever since the observatory is functioning. So then in 1971, it became Indian Institute of Astrophysics. There were also a lot of discoveries which was happening in 1899. I suppose Dipankar might be putting out some of the discoveries in solar physics happened during that time from Kodaikanal in his talk. So as we stand in 2026, Indian Institute of Astrophysics has various centers across the country. Our headquarters is in Bangalore. We have the Kodaikanal Observatory, which has completed more than 125 years of operation, and the data are all made public as well. We also have a nighttime observatory in the Kavalur called Venubapu Observatory. He's the founder director who actually formed the Indian Institute of Astrophysics from the Madras Observatory. And his visionary 2.3 meter telescope established in 1985. Then we also have a radio observatory in Gauribidanur. And we all know that the southern peninsula gets affected by the two monsoons, the southwest and the northeast. So the sky conditions are not cloudless not throughout the year, right? Some months get clouded out. So the idea was that to set up an observatory in the Himalayas where it is not affected by either of the monsoons. So that dream came to realization in 2000. And we established a high altitude observatory it's called Indian Astronomical Observatory, the setting up of 2-meter telescope there. And that has been operational for the last 25 years. And since it is very difficult to go there because it's at a height of 4,500 meters above sea level, hardly any oxygen, it's a high, dry, high altitude desert. It was also mentioned that it mandated that the remote observation should be made possible for that telescope, and that we do it from Hausakote campus. And so these are our ground stations. But this century, the Institute also embarked on two major space programs. One is building an ultraviolet telescope on the AstroSat mission, which was sent to orbit 10 years ago. So it's more than 10 years now, and it is still functioning. So UVIT and AstroSat is made by this institute. AstroSat itself is a first space observatory and operated by ISRO. And it's a milestone event which we celebrated recently. More than 10 years it's been operational, and also all the data has been made public. The next one was the coronagraph on Aditya L1 was also made by this institute. It is also completed a few years in orbit. Mind you, this is at the L1 point, which is 1.5 million kilometers away towards the sun. So that's also a very unique experiment. The data from that is also made public. Apart from that, India became a partner in the 30-meter telescope project, which is a the 30-meter size primary. So it's a very ambitious project where the primary size itself is like a football field. And that project is also coordinated by the IAA. And recently we are into setting up of a planetarium, which is actually first of the LED dome planetarium in the country. And that is coming up in Mysore. So these are our projects which are going on as well as completed. Now you may ask what is in store for the future generations, because that's what they're looking at. So the recent budget had several announcements on the major facilities which is going to come up. So there were 4 projects which is a world-class infrastructure, and it's basically mega projects announced. The first is the National Large Solar Telescope. So that will be like a 2-meter solar telescope, which will be like the second largest in the world once it is finished. And that's going to come up in Meerut in Ladakh, which is a time scale of about 5 years. The next is a National Large Optical Infrared Telescope that will have a size of about 13.7, like 14-meter class telescope. It's a mega project. It will take more than 10 years to complete it. And the third one is, as I mentioned, the Himalayan Chandra Telescope is already completed 25 years. And a lot of students and the astronomical community use that, and that will be upgraded. And that will be a first segmented mirror telescope of 3.7 meter. And we also have one more planetarium of the LED dome type coming up in Amravati. So these actually are going to be made in the country and set up in the country. And that is going to create a lot of opportunities, and we will be able to get that niche technology in the country to actually build up these futuristic systems. But also we'll be able to use these extremely complex telescopes as well as the back-end instruments to push the boundary of discovery in astronomy. So right now we lack access to major facilities through which the groundbreaking discoveries are being done. Now we will have the access to cutting-edge instruments, and this is though the project is approved now, it will actually be functional in the next 5 to 7 years, like the NLST and the NLOT. The upgraded SCT and LST will be functional by 2030, early 2030s, NLOT in the later in the next decade. So it is actually the facilities for the future generations. So this is a very, very heartening news, and we have a bright future, and whoever is interested in looking at astronomy and studying it, either through engineering or through physics and mathematics, you're most welcome. And there are a lot of opportunity in the country as well. Thank you. I stop my presentation with this.
Yeah.
And thank you for the opportunity to talk to you about these upcoming projects. And I'm pretty sure that the week ahead is going to be pretty exciting, because there will be a lot of cutting edge science which is will be discussed, and I hope that will be exciting for the entire community listening, and I'm sure it'll also motivate some of you, and I hope many of you, to take up astronomy in the future. Thank you.
Yeah, thank you very much, ma'am, for your kind and inspiring words, for creating our in-house instruments in India, in our country itself, and also the contribution of Indian Institute of Astrophysics to space sciences. Thank you very much, ma'am. So, in an era when humanity is reaching farther into space and exploring the mysteries of cosmos, the success of every mission depends not only on powerful rockets and advanced spacecraft, but also on the brilliant scientists and engineers to ensure that these missions remain connected with Earth. Our chief guest today is one such distinguished scientist from ISRO, Indian Space Research Organization, whose work has been closely associated with critical systems of telemetry, tracking, and command, which is a backbone that allows satellites and spacecraft to remain connected with Earth. Through leadership in ISRO's Technology and Applications Program, Dr. A.K. Anil Kumar contributed to strengthening the technological base that supports major missions, including Chandrayaan, Mangalyaan, and the upcoming Gaganyaan human spaceflight program. So it is now my great honor and privilege to invite our esteemed chief guest, Dr. A.K. Anil Kumar, Director, ISTRAC, ISRO, to kindly deliver the chief guest address. Sir, please.
Yeah, good evening to all from India, and good morning and good afternoon to all others who are participating in this inaugural session of the International Lecture Series, Voyage through Cosmos. Ladies and gentlemen, esteemed guests and fellow space enthusiasts, cosmos enthusiasts, cosmologists, and researchers and scientists, I am really delighted and it is heartening to be here in this lecture series in the inaugural function where our Dipankar Banerjee and Professor Annapurni both are there. And actually, I am an old man out here when we talk about the astronomy or cosmos studies, etc. I am really an old man out. But yes, since I got an invitation, I thought this is a good opportunity for me to interact with the people and to hear something about cosmology and beyond, maybe beyond universe, something. I hope that the lecture series will be very much useful for our community, astronomy community, and those who are studying about the cosmos. As we gather today, we are reminded of humanity's innate curiosity about the universe. From ancient astronomers to modern space explorers, our journey through cosmos has been awesome and inspiring. Really, when you talk about, actually, basically, I am a space scientist. I worked for ISRO for the last 36 years. And Indian space, if you consider the activities of Indian Space Research Organization and the achievements what we have already got in Indian space research. One of the major vertical is the space exploration science. How to get good science from the space rockets and satellites and space applications, which is useful for the common man of India. Now, when we talk about Chandrayaan, series of Chandrayaan missions we have done Mars orbiter mission, we have done Aditya L1 missions, first solar observatory at about 15 lakhs kilometer L1 point, from where we are getting lot of science. Many other things, megatropics, Exposat, lot of things. So we have these space missions, we got a huge volume of data from where we will able to identify new discoveries, new innovations. So, and our research students are getting benefited from that. I am thankful to Annapurni and Dipankar Banerjee. They are very closely associated with the Indian Space Research Organization in all its journey for the space exploration missions. Recently, in fact, last year when I attended a UN Corpus meeting, there were discussions about the issues for astronomers are facing when they use their optical telescopes, their radio telescopes. They are facing problem from the ground-based telescopes. They are facing problem because of the large constellations in the orbits, about 550 kilometer orbit, Starlink satellites from Elon Musk SpaceX. They have put 10,000 satellites as of now. So that is creating problem for the astronomers to watch the celestial bodies, stars, sun, etc. Very big problem. Actually, in fact, the South American countries, they brought a conference paper in UN Corpus saying that these large constellations are creating problem for astronomers. They are very much worried about that. It has to be discussed as an agenda in the UN Corpus meeting. So there were a lot of discussions. Whenever science is being brought, people are very much interested, but together with that, politics also coming into picture there. But in fact, astronomers are really facing a problem when they gaze through the optical telescopes. They are seeing a lot of streaks, but it is very difficult to now to identify the streaks are getting through from the Starlink satellites or from the whatever they are looking for the celestial bodies. So this big issue is there, and I think our people also facing same problem. This leads to the sustainability of the outer space activities. So whether our outer space activities are sustainable for in long run, because there are thousands, in fact, bigger than 10 centimeter sized objects are more than 50,000 in the space. Space means less than 36,000 kilometer orbit, which is useful for the many purposes, including communication, satellite navigation, Earth observations. So there are more than 50,000 objects are there. Out of that, about 12,000 are operational and 38,000 are defect, that is debris. So that is creating problem for the safe and sustainable operations of the utilizations of the outer space. So that is one of the issue, and it is that ramifications of the side effects of this always get into the researches of the astronomers and cosmologists and researchers in the space. They will have problem. That is one of the things we can think about it. Maybe it is very good, very critical and seriously to be thought of. Other thing is the recently we were studying about the planetary defense aspects. We know that the origin of universe we are studying. Actually, cosmologists may be trying to that only most of the things. So how universe is evolved, how it is growing, how it is, what is the way it is moving ahead. But usually we say that asteroids are the basic structure which is giving some idea about the how universe is evolved. So asteroid studies, that is asteroids, as we know that, or it is technically, theoretically proved that the dinosaurs got extincted because of an asteroid impact. And in about 100 years back, 1908, in Tunguska of the Siberia, Russia, an asteroid impacted. Impacted means it is just rubbed through, and because of the fireball happened, a long area of the forest got fired. So is there any chance that again in the on Earth, whether an asteroid impact will seize human life, or say the species of the human will be extincted like dinosaurs? There was a question. So that depends upon the planetary defense. So 2004, through our sophisticated observational facilities, it is found that an asteroid called about 340 meter sized asteroid, it was observed, that is called Apophis. It was on the collision course with Earth. And in 2029, April 13, it is expected to reach very close to Earth, about 2,000 kilometers. That is, it will be crossing our communication geobelt, and it will be reaching 32,000 kilometers near Earth. When it was found in 2004, the probability of collision with Earth was about 44 in 10.4. That means that is a big probability. Then this planetary defense took a lot of interest by the researchers, and a lot of studies were carried out. But now today, the probability of hitting an asteroid on Earth is very less, especially Apophis. But still, Apophis is coming close to Earth, 32,000 kilometers near to Earth by 29 April 13. Once it moves away, again it will be coming back in 2036. Now our space scientists or researchers, they are trying to study, trying to go very near to this Apophis by 2029 it reaches. By 2028, it's some missions are planned, and study how, what are the compositions, what are the materials, what is the exact trajectory of this, and how gravity is affecting this Apophis, etc. So that is the one other area where our astronomers are or scientists are giving lot of inputs. So let me thank the organizers, especially Bhaktivedanta Institute of Kolkata and the other organizers for inviting me for this inaugurating this international lecture series for 7 days lecture series online. And let me hope that our students, our community, cosmologists, astronomers, all are getting benefited. And I know that this conference brings together experts, researchers, and enthusiasts to share insights, their ideas, the current state of the affairs, and innovations shaping our understanding of the space and the cosmos. So let me wish all the very best for this lecture series. I declare this as inaugurated. Thank you. Thanks a lot.
Yeah, thank you. Thank you very much, sir, for your very, very important remarks on sustainability of our space activities and challenges faced by astronomers and now to human beings. So thank you. Thank you very much, sir. So now I would like to invite all our dignitaries of the inaugural session, Professor Dipankar Banerjee, Professor Annapurni Subramaniam, Dr. A.K. Anil Kumar, Professor Manoranjan Sinha, and Sri Vasudev Rao to join us for the release of electronic handbook of the lecture series. So our dignitaries can, if possible, can on their videos. Professor Dipankar Banerjee. Professor Banerjee, are you there? Yeah, I think we can start. So thank you all our dignitaries for joining. Thank you. So the handbook you can see, you can find it by scanning the QR code, and the link also has been shared in the chat box. So please click on the link to avail this very important handbook having all the details of our lectures, which is going to come along with the title, abstract. Yeah, so thank you all. So before moving further, I request all of you to please turn on your video camera, all the audience participants. So just we will take a small group photo. It's a request, so please, all the participants as well. So yeah, thank you all for joining for this photographic session. So so you can, all our participants can turn off your videos, please. So now I would like to invite Mr. Yenegu Nikhil, research scholar at Department of Chemical Sciences, ISRO Kolkata, to please give the vote of thanks. Nikhil.
Yeah, thank you, Dr. Tiwari. Respected chief guests, distinguished guests of honor, and all the dignitaries, esteemed professors and scientists, respected representatives of our partner institutes, dear colleagues, participants, ladies and gentlemen. On behalf of Bhaktivedanta Institute, it is my privilege to offer vote of thanks at the conclusion of this inaugural session of the Golden Jubilee Lecture Series, Voyage through the Cosmos. At the outset, I would like to express our sincere gratitude to our chief guest, Dr. A.K. Anil Kumar, Director of ISRO Telemetry Tracking and Command Network, whose presence today has greatly enriched this occasion. His remarks highlighted the remarkable progress of India's space program and reminded us of the importance of sustained scientific exploration and institutional vision in expanding humanity's understanding of the cosmos. We are equally thankful to our guests of honors, Professor Dipankar Banerjee, Vice-Chancellor of Indian Institute of Space, Science and Technology, Thiruvananthapuram, and Professor Annapurni Subramaniam, Director of Indian Institute of Astrophysics, Bangalore. We sincerely appreciate your gracious presence, thoughtful remarks, and highlighting the contributions of India and recent developments in the field of astrophysics and space sciences, which has helped set the tone of this extraordinary gathering. It is also my great pleasure for us to welcome the distinguished speakers, professors, and researchers who will be contributing to this lecture series over the coming days. We are privileged to have with us Professor John Schwartz of California Institute of Technology, who is one of the leading founders of string theory. Professor Avi Loeb of Harvard University, Professor Paul J. Steinhardt of Princeton University, Professor Andre Linde of Stanford University, Professor George Ellis of University of Cape Town, and Professor Wendy Freedman of University of Chicago. We are grateful that scholars whose research have played such a significant and important role in shaping contemporary cosmology have agreed to share their perspectives with this audience. We also extend our sincere thanks to other eminent members of international academic community who will be addressing this series, including Professor Ofer Lau of University College London, Professor Mario Livio, former professor at Telescope Science Institute, Professor Tim Eastman, formerly of the University of Alaska, Professor Louis Marmed of York University, Professor Luke Barnes of Western Sydney University, Professor Frank J. Tipler of Tulane University, and Professor David Dilworth. We also warmly acknowledge the presence of eminent scholars from India whose contributions continue to strengthen the nation's scientific and intellectual traditions. Professor Pankaj S. Joshi of Ahmedabad University, Professor T.P. Singh, former professor at TFR, Professor Dipankar Banerjee from Indian Institute of Science, Space Science and Technology, Thiruvananthapuram, Professor Manoranjan Sinha, IIT Kharagpur, Professor Aryan Agner of Jain University, Professor M.S. Sriram, President of Professor P.V. Sharma Research Foundation. Our sincere appreciation goes to Sri K. Vasudev Rao, President of Bhaktivedanta Institute, and Sri Varun Agarwal, Director of Bhaktivedanta Institute, whose efforts and guidance have helped bringing this lecture series into being. At this moment, it is also appropriate to remember with respect Dr. T.D. Singh, Founder Director of Bhaktivedanta Institute, whose vision encouraged thoughtful dialogue between modern science and deeper philosophical inquiry. This Golden Jubilee lecture series stands as a continuation of that vision. We also express our deep gratitude to knowledge partners, to various academic organizations that helped sharing this program with a wider academic community, which includes NRC ISRO, Ayuka Pune, PRL Ahmedabad, ARIS Nainital, CSIR CRRI New Delhi, CSIR NAL Bangalore, SESI ISR Kolkata, IIT Kharagpur, IIT Kanpur, IIT Guwahati, IIT Hyderabad, IIT BHU Varanasi, and IIT Dharwad, along with other institutes whose cooperation has been greatly appreciated. I would also like to acknowledge the program chair organization team, technical coordinators, and volunteers whose dedication and quiet efforts behind the scenes made this gathering possible. Finally, we extend our appreciation to all the participants, students, and researchers who has enthusiastically joined this lecture series. Your presence reflects the shared curiosity that continues to inspire the scientific enterprise and our life. As we begin this lecture series, we look forward to thoughtful exchange of ideas and meaningful engagement with some of the most profound questions concerning the nature of universe. Allow me to conclude with a reflection that resonates deeply with the spirit of scientific inquiry in the words of Carl Sagan. Somewhere something incredible is waiting to be known. With these words, I once again convey our sincere thanks to all our distinguished guests, dignitaries, speakers, partner institutes, and participants. I request all the participants to attend all the lecture series today and the entire week. They would be very thought provoking and would greatly enhance our knowledge and understanding of the universe. Thank you all.
Yeah, thanks, Nikhil, for this wonderful vote of thanks. So before we move to today's lecture, I will briefly go through today's schedule. So the first talk will be delivered by Professor Wendy Freedman. She is the world's leading observational cosmologist from Department of Astronomy and Astrophysics, University of Chicago, USA. She will speak on a very fascinating topic. Is there something missing from our current understanding of the cosmos? So Professor Wendy Freedman has already joined us. Okay.
Can you see my slides?
Yeah, ma'am. You are so. We have some announcements. Is it possible to unshare once, like just for a few minutes? Yeah. Sorry for that. So before we proceed, I would like to request all our participants to please scan the QR code displayed on the screen to submit your question to Professor Freedman anytime during or after the lecture. You may take a screenshot or photo of the QR code also, and the Google form link has been shared in the chat box, so you can click on the link and submit your questions to Professor Freedman. So now it is my great pleasure to introduce our speaker also. So just a few minutes. So let me introduce our speaker, Professor Wendy Freedman. So Professor Wendy Freedman is the John and Marion Sullivan University Professor of Astronomy and Astrophysics at University of Chicago and a towering figure in observational cosmology. She served as the principal investigator of the Hubble Space Telescope Key project, leading a massive international team to resolve the decades-long controversy over the expansion rate of the universe. Her precise determination of the Hubble constant ended factor of two uncertainty that plagued cosmology, provided the first accurate calculation of universe age, and serving as an observational anchor for the modern concordance model of dark energy. A fellow of the Royal Society and a recipient of the National Medal of Science, Freedman continues to define the frontier of precision astronomy. She is currently pioneering the use of the tip of the red giant branch (TRGB) method to resolve the Hubble tension, a critical discrepancy that may hint at new physics beyond the standard model. As a founding leader of the Giant Magellan Telescope (GMT) project, Freedman is also instrumental in building the next generation of super telescopes, ensuring her legacy will guide the future of cosmic discovery for decades to come. So with this brief introduction, now I would like to request Professor Freedman to please deliver a talk. Yes, ma'am. Welcome. So you can share your screen.
Let's see. Oops. Now I don't know if I have.
Yeah, that one.
That?
Yes, ma'am.
Okay. Thank you very much for that introduction and also for the honor of speaking at this Golden Jubilee. I really am very honored to be your kickoff speaker and to honor the contributions of so many people in India to the subject of astronomy. And to talk to you today about this outstanding problem in cosmology, which is the discrepancy now between the measurements that we are making in the local universe of how fast the universe is expanding at the present day. This is a topic that astronomers have been in pursuit of now for almost a century, since Edwin Hubble first discovered that there was this relationship between the velocity of a galaxy, how fast it's moving away from us, receding, and the distance from us, which led eventually to our understanding that the universe is expanding. And our measurements have continued to improve over that almost century. But this has been a very difficult problem and a very difficult challenge to overcome the kinds of systematic effects that plague the measurements of our distances to galaxies, as I will outline. But the improvement in our measurements over the last several decades, since the launch of the Hubble Space Telescope, really in the 1990s, have continued to improve and to overcome these systematics. But interestingly, as our measurements have gotten more and more precise, there has arisen this tension now between the value of the expansion rate that we measure today, quantity that we call the Hubble constant, and the measurements that are coming from the measurements of tiny fluctuations in the temperature and the polarization of the microwave background. And those measurements, the baseline of those measurements now, are coming from the Planck satellite, and the exquisite precision that now the microwave background measurements have led to this tension. If you fit the fluctuations from the microwave background, you can fit what we refer to as the standard cosmological model. That's a model with dark energy and dark matter. And you infer the expansion rate today, and it comes out to be a value lower than what we measure locally using the standard classical techniques that go back to Henrietta Leavitt and Edwin Hubble. That is the measurement of stars known as Cepheids. And we have new measurements now from the Atacama Cosmology Telescope in Chile and the South Pole Telescope that are in very good agreement with the measurements from Planck. What's very exciting in the last few years has been the launch of the James Webb Space Telescope that allows us to make measurements of these stars, Cepheids, and other types, for example, the tip of the red giant branch, at higher resolution and sensitivity than available with the Hubble Space Telescope. And this uncertainty or this discrepancy persists. So the question before us is this indicating fundamental new physics that's missing from the standard model that fits the measurements from the microwave background so well? Or is there something we haven't yet understood, uncertainties in our measurements, some sort of systematic effect? Now, can I advance? That's interesting. Yes. So our standard model of cosmology at the current time suggests that there is a component of what we refer to as dark matter. That is matter that is not like the ordinary matter in baryons that we are made out of, the carbon, nitrogen, oxygen, everything that we are familiar with, but interacts gravitationally. We see its effects by the motions of galaxies and stars and clusters and so on that are interacting with the luminous matter. The dark matter is affecting their velocities, their motions. And most of the overall composition of the universe, the matter plus energy contribution, is coming from a component that we refer to as dark energy. And this component is causing the universe to accelerate. And the question before us now is, are there cracks in this standard model? And is it broken? Is there something that we just don't yet understand? Now, if we go back and look at a little bit of the history of the subject, Edwin Hubble first measured a value of the Hubble constant of 500 kilometers per second per megaparsec. And I won't repeat those units again during the talk. But that came down in the 1950s, and in the 1960s, 70s, 80s, we began to see what became known as the factor of two discrepancy in the Hubble constant. That largely was a result of differences that were being measured by Gerard de Vaucouleurs and Alan Sandage and Gustav Tammann, values between 50 and 100. And the precision of those measurements, the error bars that each of those groups measured, was smaller than the size of the points that are plotted here. Now you can see that there are also values in between these two extremes that were published around that time. But we also have now come to understand why this discrepancy, and those came down to systematic uncertainties. That is, earlier on, astronomers were unable to correct precisely for the effects of astronomical dust. Now, this dust dims and reddens stars, for example, the Cepheids, and the detectors at the time were largely photographic plates, and those were nonlinear at both low light levels and high light levels. And also, there weren't very many objects that we could observe from Earth-based telescopes. And it wasn't until we got the Hubble Space Telescope that we could measure enough galaxies to overcome this discrepancy. Now, the red bars here are indicating where we are presently. The microwave background observations are suggesting a low value of the Hubble constant, about 67, and the Cepheid measurements tied into brighter objects, known as type 1a supernovae, are suggesting a Hubble constant of 73 or 74. And what's different is now the width of these lines are representing the uncertainties in the measurements. And so if we understand correctly the uncertainties at the current time, this would be indicating a 5 sigma difference, perhaps even larger. 6 or 7 has been a claim. And that would require then that we have new physics beyond the standard model, that something is missing from our understanding of the evolution of the universe. Now, Hubble allowed us and CCDs, charge coupled devices on the ground, to go beyond the photographic photometry. So when CCDs, these linear solid state detectors, became available on telescopes in the 1980s, we were able to make measurements at a variety of wavelengths. So this here is the distance modulus defined. It's a logarithmic measurement of the distance as a function of the inverse wavelength of the observation. So we could go from the blue region of the spectrum out into the near infrared, the I band here at 8,800 angstroms. And you can see that the distance modulus decreases as we get longer wavelength coverage. And the dashed line represents a fit to what we call the interstellar extinction law, comes from measurements in our Milky Way galaxy and other nearby galaxies. And you can see it's a very good fit to the data. And as we got mid-infrared capability, eventually with Spitzer out to 8 microns here, this interstellar extinction law provides a very good fit, and we can then correct for the presence of interstellar dust. And you can see it was a huge systematic effect when the B band observations were all that were available with photographic plates. So if you have multi-wavelength data, and in fact 2 or 3 bands is usually what astronomers have today, you can overcome this systematic. And the key project that we undertook in the 1990s, we used several methods beyond the Cepheids themselves, and the goal here was to allow for the presence of systematic effects in any one measurement. So any one of these techniques will have its own internal systematics, and the only way we could overcome the systematics overall and get a robust estimate of systematic uncertainty was to use more than one method. And to this day, that remains, I think, a very important component of these measurements. So the statistical uncertainties are represented here by the Gaussians. This is the relative probability density, and the systematics for each method are represented by the bars. And we measured a value overall of 72 with the statistical and systematics represented here, and overcame finally the famous factor of 2 uncertainty. These are recent measurements now of the Hubble constant as a function of time, the published measurements. And in red, I'm showing the measurements that are based on Cepheids and go out using type 1a supernovae, which is the method now that extends the farthest and has the smallest scatter or dispersion. And you can see that these measurements are agreeing very well with what we determined for the key project. But what has changed is that the uncertainties, the quoted uncertainties, have come down quite substantially. The points in blue here are other methods that have been published, and they are cataloged by Ian Steer. And you can see that the Cepheid-based measurements lie high with respect to the bulk of the other measurements. And this was one of the motivations for our current measurement with the James Webb Space Telescope. Our proposal was to try and ascertain, are there systematic effects in the Cepheids that we don't yet understand? And of course, if we only use Cepheids, then we're not going to discover that unless we compare those with other methods. Now, here's a comparison of this, again, the relative probability densities of recent published Hubble constant values. So the microwave background observations are here. Here are the Planck measurements. They have the highest precision to date, the smallest statistical uncertainties. And you can see that they agree well with the other measurements, South Pole Telescope and Atacama Cosmology Telescope measurements. Most of the measurements that have been made, and you can see the different methods that I've listed here, don't yet have the precision. These are 1 sigma error bars that are shown here. They're from the published papers themselves, but they don't yet have the precision to weigh in on whether or not there is a tension. And the Planck measurements are so well determined, as we'll see in a moment, that the bar now has been set very high. And it's very difficult to achieve this kind of accuracy for the local measurements, as I'll show you. Now, the one exception is the Shoes measurement here for Cepheids, and a claimed uncertainty now approaching 1%. This is our combined measurement. This is the Chicago Carnegie Hubble program from the James Webb Space Telescope that we're currently carrying out. And interestingly, we fall in the middle of these two measurements. And the question is the significance of this difference well enough determined to ascertain that we do unambiguously need physics beyond the standard model? And I just want to emphasize an obvious point. Our precision in measuring distances has improved enormously, but clearly what we need to achieve is accuracy. And what we're trying to do is make measurements over hundreds of millions of light years. And at each step in the ladder that we're making these measurements, we have to overcome systematic uncertainties. And these have been dominant in astronomy. They will continue to be dominant. It's not statistics that govern how accurately we can measure the local Hubble constant. Our program with the James Webb Space Telescope, we are using an infrared camera, NIRCam, has 10 times the sensitivity of Hubble at these wavelengths and almost 4 times its resolution. And our goal is to measure 3 independent methods and apply them to the same galaxies, all of which have been host to type 1a supernovae. So why do we have to tie into the supernovae? None of the methods locally, like the Cepheids, like the tip of the red giant branch, go out far enough in distance that they overcome the mutual gravitational interactions of galaxies that induce what we call peculiar motions, and that contributes a scatter over and above the Hubble expansion. So as we go farther and farther out, that kind of scatter decreases. It's a smaller fraction of the overall expansion rate. And so we tie into the supernovae to minimize that scatter that comes from gravitational interaction of galaxies. So we're using tip of the red giant branch, Cepheids, and a method called the JGB that we recently developed, our group. And this is something that we've been working on for decades now, trying to refine how we measure the distances to Cepheids. This has moved over from here. Somehow the resolution has changed. Sorry about that. And using facilities like Spitzer and Hubble and now the James Webb Space Telescope. Cepheids are probably well known to many of you in the audience. This is the classical way of measuring distances to galaxies that we've been using for now over a century. It's a relationship between the luminosity or log of the luminosity and logarithm of the period in days. And this is now known as the Leavitt law. And you can see there's actually scatter in this relation. Much of it is real. There is a period luminosity color relation, and the color is reflecting the temperature of these stars. They're young stars. That's an advantage. They're bright. They're supergiants, so we can easily see them in nearby galaxies. But it also carries with it some disadvantages, and that is these young stars have not had time to diffuse away from the regions of star formation where they were formed. So there's a lot of dust still, and they're in high star formation regions. So the measurement of the luminosities of these individual stars that we need to measure accurately, they're crowded, they're blended with other stars, and we can't get around that. That's where they're located. The tip of the red giant branch, these red giant branch stars offer an advantage in the sense that they're an old population, so we can measure them not only in the disks of galaxies, but also in the outer halos, where the reddening by dust is negligible and they're not overlapping with other stars. So measuring their luminosities is quite straightforward. What we do is measure the position at which these stars undergo something called the core helium flash that I will describe in more detail. And this last method, using carbon stars, Barry Madore and I discovered a few years ago that there's a population of stars, red population of stars, that have been identified by others but not used as extragalactic distance indicators. And they have a luminosity function. Their luminosity shows small scatter for this region in color, and they're bright. They're brighter than the red giant branch, which is down here. And this is not as well known as the other methods. When we proposed to James Webb, we said that we get them for free. We're looking at these galaxies to study the red giants and the Cepheids, and we'll test that method. And it turns out to work quite well. The microwave background, just to refresh your memory for those of you, and for those of you who might not know, the measurements come from tiny fluctuations in the temperature and the polarization of the background. Here's the power law of these fluctuations. And you can see that they're exquisitely well fit by a model that has only 6 parameters and is known as the cosmological constant cold dark matter model. And that is what we take to be the standard model in cosmology today. And the temperature and the polarization measurements are, again, really well fit. They determine a value of 67.4 plus or minus 0.5. And this is an extraordinarily high precision, as I have indicated. Just very briefly to show you results from ACT and SPT, that now combining all these results for the 3 different experiments. So these are done by different groups. They have different wavelength coverage. Planck is in space, the other 2 on the ground, one at high altitude, one at the South Pole. And these groups are agreeing extremely well. So the measurements by these different groups have converged for the microwave background. That is not yet the case for the local distance scale. These measurements are harder to overcome the systematics. And if we look now blown up, it's the Hubble constant is a function of time again. The measurements coming from Cepheids and the Shoes group are high. The microwave background is lower, and our measurements of the tip of the red giant branch are falling in between these 2 measurements. So there's this discrepancy between the CMB and Cepheids, but there's also still a discrepancy between our 2 groups measuring Cepheids and tip of the red giant branch. And this one would signify a discrepancy that requires fundamental new physics. This one may be telling us either about astrophysics, difference in the stars we're using, or unknown systematic effects that we haven't yet uncovered. Now, there's been a lot of activity, theoretical activity, to try and explain what could what would the implication of these results be for fundamental physics? How could we explain this discrepancy? And even 5 years ago, there were over 1,000 papers that have been published on the subject, and one paper on early dark energy here on the archive per week. And early dark energy emerged as front runner as a possible explanation because most of these other methods have already been ruled out by the exquisite data combining the microwave background, large-scale structure, and supernovae. It's very hard now to the data are very constraining now as to what are possibilities. The nice part about the early dark energy is that be tested empirically. And again, here's the Planck data, 6-parameter fit. And in 2022, the ACT data had a small indication, maybe at a 2 or 3 sigma level, that you could have a better fit if you included early dark energy. So that required a 9-parameter fit, so 3 more parameters that described when the early dark energy would come in. It would have to be before recombination, or you would already see its effects in these other constraints that I mentioned. You have to know what fraction of the dark energy it contributed, and then it would have to disappear before recombination so that you would not be able to detect it elsewhere. In that case, you could determine a Hubble constant about 71, but you couldn't get as high as 73 or 74, and at the expense of a factor of 3 increase in the uncertainty relative to Planck and 3 additional parameters. Again, this was testable. So in the most recent results from ACT in data release 6, there is no evidence for this dark energy component, and it was predicted to be maybe 20 sigma or 40 sigma if it was real. And so these authors have looked for departures from the standard lambda CDM model, but they can't find any evidence for it in this better data. So just to summarize the current status of theory, a lot of effort has gone into it. There's no convincing explanation for the tension. Some models can achieve 70 or 71, but it has proved to be exceedingly difficult to get as high as 73 or 74. And one problem is that you trade off the tension in the current expansion rate with large-scale structure constraints, the so-called sigma 8 parameter. And if you try and improve the Hubble constant tension, then you make the large-scale structure problem worse. And that by itself seems to, the experiments are showing that perhaps this is not as significant as once thought. Okay, so why is it so difficult to measure an accurate value of the Hubble constant locally? And as I mentioned, there are now 3 steps to going out to the type 1a supernovae. We have the nearby galaxies where we can measure a geometric distance to the galaxy. There are only 3 galaxies for which we can do that. There are Cepheids and tip of the red giant branch, for example, in the Milky Way, where you can measure direct parallaxes using the Gaia satellite. There's a galaxy, NGC 4258, that has a massive black hole about which water masers are orbiting, and you can get its geometry and distance from that. And there are eclipsing binaries in the Large Magellanic Cloud. So these are the galaxies that set the calibration, the anchors. With the type 1a supernovae, we can measure the relative brightnesses of these objects, the relative distances, same with the Cepheids and tip of the red giant branch, but we have to know the absolute luminosities of these stars to get the Hubble constant and to get their distances. And so there are only 3 objects here that we can use. That's not a high statistical number of galaxies to set the whole 0 point. You need to keep that in mind. We move then to the realm of Hubble and James Webb, where we can measure Cepheids and tip of the red giant branch stars in galaxies that have had type 1a supernovae. So then we set the scale for the supernovae. And just want to point out here the tip of the red giant branch in the halo, you can see how well separated they are, and the more difficulty in measuring in the disks of galaxies where you have dust lanes and high star formation rates and crowding and blending of stars and so on. So statistically, there are about 3 dozen galaxies that we can measure in this middle rung, and not all of them are well measured. The ones that are farther away are more of a challenge. And now we're getting hundreds, approaching thousands, and with Rubin approaching millions of supernovae. So there are no statistical uncertainties in the largest distance rung. But again, it's systematics that we need to be concerned about. And if we're going to measure a value of the Hubble constant at 1%, Planck now has set the bar at they're measuring sub 1% precision. But if we're going to ascertain if there is new physics, we need to ensure that at every step along this way, the systematics are less than 1% if the overall uncertainty is to be at the 1% level. And that is a very big challenge. James Webb, for those of you who may not be familiar, it's out at a L2 orbit. That's about 1 million miles, 1.5 million kilometers from the Earth. And it's a 6.5 meter telescope compared to Hubble. It's a 2.5 meter telescope, and it's been optimized for the infrared, which is a huge advantage, again, for dust, for the Cepheids, for the tip of the red giant branch, and carbon stars. These are red stars, and so it's ideal for measuring distances. Here's an image of a Cepheid taken by Hubble by the SHOES group. It's at a distance of 20 megaparsecs. The Cepheid's located in the red circle. The Cepheid has been discovered in the optical, where the amplitudes of Cepheids are largest, but the distance measurements come in the infrared, again, so that dust is less of a problem. And you can see the challenge here and the difference that JWST makes in terms of resolution and sensitivity if we're going to accurately measure the luminosities of these stars. And 60% of the SHOES sample lies at a distance greater than 20 megaparsecs. The problem only becomes more challenging as you move out in distance. And here another example, and you can see these stars are embedded in regions where there are other stars, and James Webb is going to allow us to make much more accurate observations. So I will only show you some results from the tip of the red giant branch today. That's the method for which we have the most observations of supernova host galaxies. And just briefly mention that we are blinding our data, so we don't know as we're doing the analysis what the distances are and what the Hubble constant is. And that's new in this local distance scale, has not been done before. The physics of the tip of the red giant branch, I'll only briefly say, it's the only method for which we can go from first principles and understand the underlying physics, which another advantage of this method. These are stars that are burning hydrogen in a shell about a partially degenerate helium core. They're climbing what is known as the red giant branch, and when they reach a temperature of about 100 million degrees, they can start to burn helium in a stable way. And this occurs, there's a core helium flash. This has been studied theoretically by many groups, and over a range of metallicities here, the Z or the Z stands for metallicity, very small changes, and we can empirically calibrate this. So it is an excellent standard candle. What we do in practice is measure the luminosity function, how many stars as a function of luminosity there are, and we're looking for a discontinuity or the first derivative of this luminosity function that characterizes where this core helium flash occurs. Here is just an example of where we pointed the NIRCam, the near-infrared camera on JWST, allowing us to measure the halo out in the outer parts of the galaxies where the tip of the red giant branch stars are, and the disks where the Cepheids are. And we now have overlap between our Hubble program that we carried out earlier and JWST, and they're agreeing very well. And in fact, the SHOES measurements, which were discrepant in 2019, now agree with our tip of the red giant branch distances from Hubble, and that have now been confirmed with JWST. So there's been a convergence of these measurements, which is really nice to see. In terms of the supernovae, this is a project, the Carnegie Supernova Project, that I carried out. Mark Phillips and I were co-principal investigators while I was at the Carnegie Institution. And we're using 3 different aperture-sized telescopes at Las Campanas in Chile, depending on the luminosity of the supernova. We weren't trying to find the supernovae. That was being carried out by many other groups. But what we were trying to do was ensure that we had wavelength coverage. So we had 9 different filters from the ultraviolet into the near infrared, and we ensured that we had very good cadence, very good coverage of these supernovae. And the experiment again was designed so that we could test for systematics like dust, like environments of the supernovae themselves. And we also got spectra over time so that we could make corrections for the so-called band effects as we go out in distance. And all of these data were input into Markov chain Monte Carlo analysis, fitting these light curves that allowed us to determine the Hubble diagram. This is the distance modulus, again, that I mentioned, as a function of the logarithm of the redshift relative to the cosmic microwave background. So we have about 300 objects, and it was carried out in 2 phases, CSP 1 and 2. And we used 2 different Markov chain Monte Carlo type analyses. This is our likelihood function for those experts in the audience who will know what we needed for this MCMC analysis. And what we found was a Hubble constant of 70 with an uncertainty of about 3%. And this is a conservative uncertainty, which we think, given the level of understanding of the current systematics, is a reliable, reasonable estimate of the current uncertainty. Do we now have a robust estimate of the Hubble constant to 1% and the 5 sigma and now even 7 sigma now claims in the literature? And I think if we are at 5 sigma or 7 sigma, how can we explain the Hubble tension by anything except for new physics? Now, 5 sigma is the gold standard in particle physics. It's the level at which one would say in an experiment that you have put your uncertainties then at a level that 99.9999% that you are have made a discovery. But I think there are reasons to keep an open mind still on interpreting the tension. It may be there, but I think we need to ensure that we have understood all of the potential systematics. And I mentioned early on that the entire local distance ladder rests on the calibration of 3 anchors, the Milky Way Large Magellanic Cloud and this galaxy NGC 4258. So if there are systematic errors that are at the current time not well understood, the Hubble constant will shift for all these methods, Cepheids, tip of the red giant branch, and these JAGB stars, but also methods that are calibrated by them. They will all shift, the Tully-Fisher relation, surface brightness fluctuations, the masers that are based on 4258. And it's a small sample statistically. Again, there are only 3 galaxies. These measurements are difficult and challenging. In some cases, only a single group has made the measurements, and we'll see in future how those hold up. There have been a number of cases in the recent literature where groups have reanalyzed the photometry, our own and the Shoes group, doing photometry in these crowded fields with new cameras, like for the James Webb Space Telescope. We're uncovering uncertainties in the cameras themselves that are large, and applying the same techniques as we did with Hubble. We uncover difficulties in doing that. And so there have been a lot of changes that have occurred that are at the level or even greater than the uncertainties, the total uncertainties. And so it's important to realize that even subtle shifts now, a few hundreds of a magnitude, do translate into differences in the Hubble constant that are at the size of the whole uncertainty. So we still have work to do to nail down this calibration. Doing photometry over these distances at the 1% level with dust, with crowding, with our understanding of the instruments and systematics in the objects themselves is, again, very, very challenging. And it's important to realize that measurements in cosmology are generally limited by systematics. It's not statistical uncertainties, but even we have statistical uncertainties in the nearby universe with the numbers of anchors and even the middle rung. And that, in interpreting the formal significance, differs from particle physics, which is dominated by statistics. So you can work with your instruments in a lab in a way that we can't with these astrophysical objects that are at enormous distances from us. So interpreting a 5 sigma result is different. Here's the tension, the definition of the tension. We're looking at the difference in the two values of the Hubble constant from Planck here and the Cepheids, divided by the uncertainties of some of the squares of the uncertainties. And the tension with Planck then would be 5 sigma. And just as an example, I'm not saying this is what is the case, but to illustrate, if you had corrected the Cepheid distances from the 2022 to 2016, the Hubble constant would have come down to 71. And if you include the supernova uncertainty and include it as an uncertainty rather than as a correction, then the tension drops to 2.4 sigma. So we do need to understand the systematics in the supernova measurements and also in its corrections for the Cepheids. We need to understand those at the 1% level, and I would argue we're not yet there. I'm keeping my eye on time. I just want to say that a number like plus or minus 1%, we have to be aware that there's a chain of choices in the calibrations, the data sets, the priors, the modeling assumptions, and those are continuing to evolve over time. And until we see, I think, that those have converged, interpreting this as 5 sigma, i.e. level of a discovery, I think we have work to do. Let me just mention what we're currently trying to do. We're doing blind now stress tests of the tip of the red giant branch and supernova measurements. We have new measurements from Hubble as well as JWST, and those have all been reduced with improved techniques, analysis techniques that have been evolving with time to deal with crowded fields where the Cepheids and the tip of the red giant branch stars improvement in the photometry. And we do this blinded analysis again. Different parts of our team reduce the data, and we don't talk to each other until everything is complete. We're also, Suhail Duan is leading an effort from the supernova end where we're comparing different surveys, people of different calibrations, different ways of fitting the light curves, different networks, calibration networks, different dust maps, different ways of treating these peculiar velocities. And so again, we're doing this blind. We're fitting all of these different models. You can see sometimes the models fit well, sometimes they don't. And all of this is going to be made available on GitHub. You can choose or you can test how these different surveys and the different light curve methods are working, different dust laws and so on. So this will all be available on GitHub so that you can play yourself and see how these things are affecting the results. And we're trying to get a handle on quantifying the overall systematic uncertainties again. So I'm going to leave you with the relative probability density measurements. Again, this is from Planck, the microwave background measurements at about 67. These are recent results from DESI. And here are our results from the Chicago Carnegie Hubble program at the current time. We're continuing to increase the sample size, and statistically, those measurements will improve with time. And let me just make a few final comments. And I don't want to leave you with the impression that these measurements aren't improving. They are improving enormously if we think back to the uncertainties at a factor of 2, and then Hubble, where we could measure things at the 10% level in the key project. We're now going from this uncertainty of a factor of 2 to a factor of a few, 3% or better, the goal of 1%. And at this time, it might not be sufficient to provide unambiguous evidence for new physics, but we're getting there. And there are a lot of new data that are coming, both from JWST, and also there'll be future data from the Rubin telescope, Roman, which will be launched soon. Rubin, which has just started its analysis and survey coverage of the sky. And then eventually other techniques that we hope will provide enough statistics to test the local distance scale measurements based on luminosities of stars, but measure those independently. And so let me just say finally that based on our data from Hubble and James Webb, using Cepheids, the tip of the red giant branch, and the JGB method, all calibrating type 1a supernovae are consistent now with a value of 70 and an uncertainty of 3%. And I will stop there. Thanks very much. Leave time for questions.
Yeah. Yeah, thank you, Professor, for your brilliant talk. And you have highlighted various points in reducing the uncertainty of the measurements. So yeah, thank you once again. So I would like to remind our participants to please submit your question by scanning this QR code, and the link has been sent to the chat box also. You can submit your questions there. So we have some questions coming. So I will share some few questions here, ma'am. So yeah. So we have got the first question from Dr. Bharat Pandey, saying that my question is, recent observation from James Webb Telescope suggests that some galaxies formed much earlier than predicted by lambda CDM model. Do you think that these observations indicate a need to revise our standard cosmological model?
So I'm not sure which methods the questioner is referring to. I think in aggregate, the current measurements that suggest that there is a need to essentially add new physics are at the level of uncertainty that at the current time actually don't resolve in an unambiguous way whether there is a tension. I think what we will see in the next few years as these methods improve in statistics and people get a better understanding of the types of systematics that may be affecting those measurements, this is going to clarify. And at the current time, the uncertainties, in my view, are insufficient to say with certainty, say at the 5 sigma level, whether or not we need new physics. But that's coming. There's a lot of work that is, I think, going to happen in the next few years, and this should be clarified quite substantially.
Thank you very much. So we have another question. So this question is by Hariom from GGTC Agast Muni Rudraprayag from Uttarakhand. Is asking that if the universe is expanding, how is it possible that the two galaxies, Andromeda and the Milky Way, are coming close to each other?
Yeah, the Milky Way and Andromeda are very close to each other, so the mutual gravitation is such that we will merge with the Andromeda galaxy in the future. And interestingly, when Edwin Hubble first discovered the expansion or provided data that indicated the universe is expanding, there was a handful of galaxies that are nearby to us, and also galaxies in the Virgo cluster, a nearby cluster that are their motions, their peculiar velocities indicate that they're coming towards us. But the vast, vast, vast majority of galaxies are receding, and we do understand the reason why. These nearby galaxies are their mutual gravitation is such that they're approaching us rather than receding. But the bulk of the universe appears to be expanding. It is overwhelming evidence, and the nearby galaxies are an exception. There's a handful of them.
Yeah, thank you very much. So we have got our third question by Dr. Soubik Roy. Is from Technoman Salt Lake College from Kolkata. So your slides showing different measurements. So some curves to be mesocutic, some to be platicutic, and some to be leptocutic curves. Which of these measurements give best approximations?
So I think at the current time, the data are such that what we see as evidence for the expansion can be fit very simply as a uniform expansion of the universe. And I think what we're trying to do, particularly in the more distant galaxies, is to see how we deviate as a function of time or redshift. And that's how we get evidence for the accelerating universe. And so what we're trying to do is understand how the universe is evolving over time. And so the more distant measurements indicate that it isn't simply a uniform expansion, but that the effects of gravity, so the presence of dark matter and also the dark energy affect those results. And now we're actually, there are groups, the DESI group, and people measuring supernovae. And so the measurement of large-scale structure plus supernovae together seem to be indicating that might not just be a simple model. We may have not just a simple cosmological constant, that there may be evolution of the dark energy as a function of time. So many groups now are trying to understand the systematics again, because statistically the large scale structure measurements were now approaching 1 million galaxies. So the statistical uncertainties are negligible, but again, comes down to systematics. So we are trying to understand, in fitting the expansion, how that could change as a function of time. So it might just not be a simple cosmological constant as Einstein, the general theory of relativity would allow in Einstein's gravity, this repulsive form of gravity, but it might be more complicated. So there are a lot of efforts now to try and see how this is evolving as a function of time, and it's something that we will see in future.
Yeah, thank you, ma'am. Thank you very much. So we have got our question from Roy from Asutosh College, Kolkata. So he's asking, when the tip of the red giant branch stars data is used to measure the expansion rate is around 69 or 70, a drop from the Cepheid value of 73. Do you believe the TRGB data is hinting that the Hubble tension might just be a systematic error in how we read Cepheids, or is it entirely an undetected unknown variable?
I think time will tell how this will resolve. I think one of the nice things about the tip of the red giant branch is that the systematic uncertainties in measuring the luminosities are smaller than they are for the Cepheids. The stars are out in the halo, so there's negligible dust, as I mentioned. The crowding problem is not an issue. In terms of the abundances, the metallicities of these stars. In astronomy, we talk about metallicity being anything heavier than hydrogen, helium, or deuterium. And it's so the metallicities, it's a smaller effect. We can also calibrate it directly, empirically, to see as a function of color of the star, which would be representative of a change due to the underlying metallicity. It's more complicated for Cepheids. Cepheids, again, they have higher reddening. The photometry is more challenging because of the crowding effects. We can't directly measure the metallicity of Cepheids. We have to do this in a way as a proxy using the metallicities of hydrogen, ionized hydrogen regions known as H2 regions. And then we infer from that this is the effect for the Cepheids. And so there are these challenges. There are more challenges for the Cepheids, I would say. But I think it's too early. I think the tip of the red giant branch results are consistent with the microwave background, but they're also consistent with the Cepheid results and at the 2 or 3 sigma levels. So we'll have to see with time how this goes as we get more tip of the red giant branch measurements, as we test the Cepheids going farther out where the challenges are greater. And but at the current time, I think it's too early to say. But we can't rule out that the standard model will survive. The tip of the red giant branch measurements are consistent with the microwave background at the 2 sigma level. And I think that's interesting. But it's too early to determine unambiguously. And again, we have to pay attention to the systematics, and we have to ensure that our estimates of the uncertainty are correct. And we have to constrain those uncertainties. And I think we have work to do, all of us, to get to that place.
Thank you, ma'am, for your insightful answer. So we have got another question by Silpa. She's a research scholar at SB NIT Surat. She's asking that which theoretical model and the data set you have used in calculating Hubble constant for the recent measurement of Hubble constant for comparable results with other models that you have discussed? I think question seems somewhat yeah.
So, as I mentioned, the cosmic microwave background observations are very well fit by the standard model, the lambda CDM, cosmological constant plus cold dark matter model. So it's a model that has dark matter and dark energy. And that model is predictive. You can fit the fluctuations in the microwave background and then infer what the expansion rate would be today. And it's, measuring that inference of the Hubble constant and comparing it to what we can directly measure locally using stars like the Cepheids and the tip of the red giant branch tied into the type 1a supernovae. And as you could see from those plots of the microwave background fluctuations, that model fits those data exquisitely well. It's actually it's staggering. It's very surprising to me how difficult it has become to change the standard model. I mean, all these theoretical efforts over, 1,000 papers that have tried so hard to deviate from lambda CDM. Now, there are these hints, the DESI results, that there might be evolution in the dark energy as a function of redshift, and we will see how that comes out over time. But we just need to keep in mind that how would we test this lambda CDM model, right, that fits the microwave data so well? That's at high redshift early in the universe. Well, we would make a measurement locally and compare with what the lambda CDM model is predicting and see whether they agree. And right now, they don't. And the question before us is, how well do we understand the uncertainties, particularly in the local distance measurements? Because as we saw, the microwave background measurements already have converged. The different experiments are agreeing at the percent level, and we aren't there yet with the local measurements. But we're making huge progress in trying to get there. So again, what we're doing is testing the model by improving the accuracy, not just the precision, but the accuracy in the measurements of the local Hubble constant.
Yeah, so thank you, ma'am. So we will take a last question here. So Professor Loeb, just wait a few minutes. We will start the session. So just we have some questions still. So it is from Karthik Asokan from Visvarya National Institute of Technology. So I just wanted to ask you about the ACT data showing a better fit if included the early dark energy model. But to increase the H0 value, many papers seem to be compromising on empirically validated observation, such as the sound horizon, way too much. What do you think about the credibility of such methods, and how do you view early dark energy as a solution for the tension? I mean, we need to model within a certain error range and not straight too much away, right? So, ma'am, your comment, please.
Yeah, the results coming from ACT used to be that the large scale structure measurements, you had to calibrate them somehow with the sound horizon measurements that would come from the cosmic microwave background. And I think the measurements of or the hints of early dark energy in the early ACT measurements, there was this tiny 2 or 3 sigma discrepancy with the lambda CDM model. And I think what was really nice about these experiments is that, again, subject to empirical tests, if that had been a real measure of the early dark energy, then it would have increased in its significance in the DR6 data, where they had much more sky coverage and better statistics. And there were estimates at the time that that could end up being a 20 sigma, and some people even said 40 sigma effect. And that did not show up in the data. It's not there. Now, it's not ruled out. You could have some extreme model eventually. Maybe something will be discovered that again, with the caveat that you're adding lots more parameters to fit the data and your uncertainties go up as you do that. But it is a clean test, right? There's a prediction. Okay, if there was early dark energy and if this 2 or 3 sigma effect persisted, then there would have been evidence for the early dark energy, and we don't see it in the ACT data. They tried to fit many different extensions to the lambda CDM model, and none of them provide a better fit. And that's true of the Planck data, it's true of the South Pole Telescope data. They're remarkably consistent with lambda CDM at the current time. I think it's still an open question, but the predictions, I mean, as I said, it showed you the types of models that people have been considering. People have been scouring and trying to find evidence for or explanation for what the Hubble tension could be. And it's kind of remarkable, I think, how difficult that has turned out to be to actually find a reason why the Hubble constant would be higher. Doesn't mean that we won't eventually find a solution there, but there's no obvious solution, and it's certainly not for lack of trying. So again, we will see with time. I think that the theoretical side of this right now is not favoring that the Hubble tension will be real. And I think the data right now are not sufficient yet to either rule in or out whether or not additional physics is needed. But as I keep stressing, in order to claim that there is this tension, we really need to do better at understanding potential systematics. So the fact that there is a difference in the local universe in the most precise measurements that are being made, and I should say that so none of these other techniques, I hinted at that when I showed the probability distributions of the other methods. Most of them are not at the 3% or better level. They're 4 or 5 or way higher uncertainties. And so they're not yet weighing in on whether that tension is real. And many of them depend on the Cepheid distance scale. And if the Cepheid distance scale has systematics in it, they will all shift. So until in the local distance scale, we are able to show that we have converged, that we understand the calibrations of supernovae, and that right now we're still trying to understand. It's part of the motivation of our new blind test, is to understand where these differences in the supernovae are showing up. So we have work to do, is what I would say, and we'll see where it ends up.
Thank you, Professor, for addressing these questions with such a depth and clarity. So we still have many more questions from the audience, but due to limited time, we have to conclude. So on behalf of Bhaktivedanta Institute, I would like to once again express our sincere gratitude to you for sharing your insights and wisdom with us today. So your lecture has given a deep insights into that understanding of universe, and we are really grateful. So thank you very much, Professor Freedman.
Thank you again for the invitation.
Bye.
Bye.
So now moving forward with today's program, we have another fascinating talk lined up, and our next speaker is Professor Loeb, who has joined us already. So we are truly delighted to have you, sir, with us today. Welcome. So Professor Loeb is going to talking on searching for extraterrestrial technological artifacts near Earth. And before we proceed further, I would like to once again request all our participants to please scan the QR code displayed on the screen to submit your questions to the speaker anytime during or after the lecture. So you can take a screenshot or photo of this QR code, and link also has been shared in the Google this chat box. You can click on the link and submit your questions. So before inviting our professor for the lecture, I will just give a brief introduction of him. So Professor Abraham Loeb is a Frank B. Baer Professor of Science at Harvard University. He received a PhD in physics from Hebrew University of Jerusalem in Israel at age 24. Led the first international project supported by the Strategic Defense Initiative 1982 through 1988, and was subsequently a long-term member of the Institute for Advanced Study at Princeton. Loeb has written 9 books, including most recently Extraterrestrial and Interstellar, as well as over 1,000 scientific papers with H index of 133 and I10 index of 631 on a wide range of topics, including black holes, the first stars, the search for extraterrestrial life, and the future of the universe. Loeb is the director of the Institute for Theory and Computation within a Harvard-Smithsonian Center for Astrophysics, and also served as the head of the Galileo project. He had been the longest serving chair of Harvard's Department of Astronomy and the founding director of Harvard's Black Hole Initiative. He is an elected fellow of the American Academy of Arts and Sciences, the American Physical Society, and International Academy of Astronautics. Loeb is a former member of the President's Council of Advisors on Science and Technology at the White House, a former chair of the Board on Physics and Astronomy of the National Academics, and a current member of the Advisory Board for Einstein Visualize the Impossible of the Hebrew University. He chaired the Advisory Committee for the Breakthrough Starshot Initiative and served as the Science Theory Director for all the initiatives of the Breakthrough Prize Foundation. In 2012, Time magazine selected Loeb as one of the 25 most influential people in space, and in 2020, Loeb was selected among the 14 most inspiring Israelis of the last decade. In 2025, Loeb was ranked number 3 in publication record and impact of research among all astronomers worldwide over the past 5 years by Scholar GPS. Loeb's latest TED Talk was amongst the top 5 most popular TED Talks in 2024. So with this brief introduction, now I would like to request Professor Loeb to please deliver your talk. Welcome, sir.
Thank you so much. It's a great pleasure to join you all. And I really hope that the young scientists that are listening to this presentation will make discoveries that my generation of scientists failed to make. Because I do believe that the best is yet to come. And another comment that I would like to make is that, and let me start by sharing my screen so you can see that, is the following statement that the foundation of science is the humility to learn.
Sir, your screen is visible to us. You shared the screen?
Yeah, I did, but let me try again. Is it now?
Yeah, perfect.
Okay, thank you for letting me know.
You can do the full screen if.
Yeah. So the statement that I would like to make is that the foundation of science is the humility to learn. It's not the arrogance of expertise. And often what you find in academia is experts that are pretending to know the answer in advance, and I don't think that's the point of doing science. The other thing I would say, and that's in continuation to the previous talk that you heard from Wendy Freedman, a very good friend of mine, is that all the textbooks about the universe, and that includes two textbooks that I wrote, they always regard the universe as being made of matter and radiation, and as a cold and lonely place that we feel no emotional connection to as scientists. But in fact, if we do find an intelligent civilization out there, everything will change, because we would feel that we have siblings to our family of intelligent beings, and that would mean that we might, if they visit us, we might want to visit them. We would feel connected to the universe. It will not be just a question of finding the budget of mass in the universe and figuring out what is the Hubble constant. Actually, there would be more personal relationship between us and our cosmic neighborhood. It's sort of like finding a neighbor in your street that you can connect with. And so far, we haven't done enough to find that neighbor. And so what I would like to discuss is a subject that I believe should be part of the mainstream of science. It's not as of now, and it's the search for extraterrestrial technological objects near Earth that are sort of like packages in our mailbox. And I will describe in part the work that is being done in the Galileo project that I'm leading, that includes about 50 researchers. And so let me start with a few comments about the art of doing science. So most important in doing science is the evidence, because people can tell you a lot of stories. And by that, when I say people, I don't mean just crackpots, people that you can't trust in, that provide you with misinformation. I also mean the mainstream of theoretical particle physics. The mainstream of that for 50 years has been telling us about extra dimensions, string theory. We haven't found a clue to that, no experimental evidence. There is no experiment planned that would test string theory in the next century. And also the theory is not unique, doesn't make a prediction, doesn't explain the Big Bang, doesn't explain what happens in black holes. We don't have that. So stories are often being told to us, but the only way to make progress in our scientific knowledge is by evidence, experimental evidence, because that's the only way to basically remove ideas that do not apply to reality. Our imagination can think about an infinite number of possibilities that reality may take. And the only way for us to learn something new is by excluding, by putting limits on our imagination through experimental data. That's the key for doing science. But as you can tell, it's not fully understood right now within the mainstream of theoretical particle physics for 50 years. So scientific evidence is key. And fortunately, in astrophysics, we have a lot of it. So this is an example of a beautiful image that was obtained by the Hubble Space Telescope in December of the interstellar object 3I Atlas, and I will speak more about it. But when you remove the circularly symmetric part of that image around the nucleus of the object, what you find is evidence for 3 jets that are symmetrically spaced from each other on the sky, and another prominent jet, 4th jet, propagating towards the sun, an anti-tail. Certainly not what we expected for a comet. And that's the kind of new evidence that observations can provide us with. Even though everyone talks about it being a comet, well, it's a bit peculiar. There is this symmetry among the small jets around the nucleus, and I'll talk more about it. The other part of doing science that I currently benefit from is the interest that a lot of artists have at the frontiers of science. So this is one of them, Greg Wyatt, who donated 2 bronze sculptures to my office. This is an image of my office that became a mini museum over the past year. He also donated 51 watercolors to my office that include the portraits of famous scientists and philosophers, including also what they said about science. And so this donation from him actually makes my life much more beautiful. And he also gave me the foundation of a new bronze sculpture that I returned to him, and that will be titled The Alien. I tried to imagine what an alien would look like. But there are many more artists. There is one that donated this beautiful piece that you see at the bottom of the middle panel here. It basically says "History Awaits." It's a painting that I received from an artist in Florida. It's actually just behind me in this room. I also received on the left here, you see an art book that was made by a class in Brazil, and the teacher sent it to me, inspired by my essays on extraterrestrials. And on the right side, you see a book of poems that was written by a poet in New Zealand that's sent to me. All of these are indications for how inspiring science can be to artists. And frankly, I find artists much more open-minded to innovation, to new ideas than the scientific community. And here is another artist. He is a songwriter from the United Kingdom who wrote a song named Oli Swan, wrote a song, Aliens Are Real, and he asked me for a blurb that would accompany the release of the song. So let me just play this song just for a few seconds so you can listen to the words are on the right-hand side.
Sir, please share the sound. We are not able to hear. I think the audio is not shared. Sir, excuse me.
Okay, it goes on and on, but basically the idea is aliens are real. And the other part is, of course, public outreach. That I write an essay every day on medium.com. So you just find it you can subscribe for free. It's avi-loeb.medium.com. And it's about the latest updates in science that in my research. I have 140,000 followers on that. And also I wrote some popular level books that became bestsellers that you can see on top here. And recently I started a YouTube channel because there were fake AI generated videos about me speaking in my voice and in my image. And I decided to fight them by creating my own content on YouTube. So there is an official YouTube channel that you can also watch. Another part of public outreach, a few months ago, I was invited to a NASCAR car race in California. You can see one of the cars on the left here, and the racer decided to put my image and 3i Atlas on top of the hood of his car. And I told him it's a great compliment for me, but not for 3i Atlas, which is moving at 600 times the speed of his car. And also television interviews, you know, the one real benefit of those, and I had 8 of them last Friday, is that I get emails from parents who tell me that their kids decided to become a scientist after watching me on television. And to me, that's the biggest reward that I can get. Because if we bring open-minded young scientists without prejudice into science, they might actually resolve and pursue many of the mysteries that my generation failed to pursue. So when people often say that extraterrestrials, you know, having another intelligent civilization is an extraordinary claim that requires extraordinary evidence, I often say that this is not extraordinary because it's an ordinary claim. We believe that we came about on Earth out of a soup of chemicals that existed in the early Earth. And the same conditions are realized in billions of Earth-Sun analogs within the Milky Way galaxy alone, based on the latest census of exoplanets. So, you know, it's very likely that there was something like us, or even better. You know, there must have been a better, a more accomplished space entrepreneur than Elon Musk since the Big Bang 13.8 billion years ago. This is an ordinary claim to say that under similar circumstances, you end up with similar outcomes. And therefore, that requires ordinary evidence. So if we, you know, usually people make this argument in order not to fund any search. And I say, well, without searching, you will not find anything. And actually, are we alone is the most romantic question in science. When you go on a date, you better aim high, not low. Right now, the mainstream of the astronomy community is willing to invest $10 billion in the Habitable World Observatory, searching for the biological markers of microbes, the chemicals in the atmospheres of exoplanets that may indicate microbial life. And that's aiming low. You know, of course, when you go on dates, the most common partners that you may find are mediocre. And obviously, microbes are very common, but they are mediocre. And I would much rather meet a more advanced, a more intelligent being than meet a microbe as a dating partner. And so my point is, of course, you can search for microbes, but it's very challenging to find evidence for them. And it might be easier to find evidence for technological gadgets near Earth if we only do the search. So without funding this, we are basically maintaining our ignorance. Now, Enrico Fermi asked, where is everybody? And if I were next to him in 1950 at lunch in Los Alamos, I would put my arm around his shoulder and say, Enrico, this is a question that every lonely person asks. And what you tell a lonely person is, don't be so presumptuous. You're not that attractive. They will not necessarily be next to you at lunch when you want them to be. You need to search for them. That's what you tell a lonely person. Enrico didn't build any telescope. So this is completely inappropriate, especially given also the cosmic scale of time and space, where the Milky Way galaxy is tens of thousands of light years in size and about 10 billion years in age. And why would the visit happen exactly when Enrico is sitting for lunch? Maybe there was a visit 10 million years ago or 100 million years ago. Recorded human history is only 8,000 years old. And the possible answer to where is everybody is right here. Because we haven't really recorded our history over cosmologically significant timescales. And in fact, even now, the US government, the Office of the Director of National Intelligence, delivered 3 reports to the US Congress talking about objects in the sky that they cannot identify. They call it unidentified aerial phenomena. And it's, of course, their day job to monitor the sky and in search for technological objects that are human-made by adversarial nations that are engaging in espionage, for example, over the sky of the US. So they monitor the sky. I mean, those kind of objects will not be identified by astronomers that focus on distant galaxies. Astronomers would never pay attention to anything flying across the sky close to Earth. And so the US government potentially will be the first to notice such things, given that the military budget is about, the defense budget is about $1 trillion a year. There is a huge amount of resources allocated for that, much more than the resources given to NASA or any other space agencies. Now, actually, former President Obama recently appeared on a podcast a few weeks ago, and he said, aliens are real. When he was asked about it, he said, yes, I believe aliens are real. And he said the truth is that when he came into office, he asked, is there any lab somewhere where one can find the specimens or other artifacts related to aliens? And he was told there is no such lab. But he just believes that there is some indisputable evidence that something unusual is happening near Earth based on what the intelligence agencies were telling him. Now, he tried to backtrack from that statement a few days later because there was a huge interest in the public in what he said. And then current President Donald Trump said that Obama should not have said what he said because this is classified information. And that's strange, right? He could have said that there is nothing behind it. But and then President Trump directed the Pentagon and the intelligence agencies to release government files that are related to alien and extraterrestrial life, unidentified aerial phenomena, and all information connected to these highly complex but extremely interesting and important matters. That's what he said. So we shall see if that will happen in the near future. But it's interesting because it means that there are things that are observed near Earth that are not fully understood. And the last people to attend to that are the scientific community researchers, and which is strange. I mean, the government doesn't have time to hallucinate. They're really engaged in national security. And so you would expect scientists to say, well, that's a serious matter that, the intelligence agencies cannot figure out things, and we should help national security by trying to figure out things. And if it turns out that they are extraterrestrial, those things, you know, it's the biggest discovery ever made by science. So that's common sense, right? And that's what I advocate through the Galileo project, but it's rejected by a lot of scientists. So the Galileo project is a project that I'm leading from Harvard University, and we're building observatories to monitor the sky and basically not wait for the declassification of information from the US government, but rather look up. I mean, if there is something out there, we should be able to see it. And so, in fact, just recently, about a week ago, we asked the public to help us with identifying objects in our images, because we see a few million objects per year, and we want to train an artificial intelligence system to identify those objects, especially those that are familiar, like drones, balloons, airplanes, satellites, helicopters. And for that, we need to establish the ground truth. And so we are asking the public to help us establish the ground truth by looking at our images. And we will use that to train our AI systems to look at the full data set based on the training data set of the ground truth. So we have currently constructed 3 observatories, one in Massachusetts, one in Pennsylvania, and another one in Nevada. The most recent one is in Nevada, and it has 3 units, that one of which is on top of Sphere in Las Vegas, which is the biggest entertainment center in the world, 100 meters in radius. You can see it in the top left. And so this is the Sphere, and I went there actually last summer to install that observatory. And here you see me standing inside of it. And on the left, you will see the difficulties, the challenge we had in basically not knocking our head against the pipes that are up there when we installed the observatory there. And most recently, actually just last month, there is a new film that came out, Marty Supreme, with Timothée Chalamet. And they did the promo. I mean, it's about a ping pong player. Timothée Chalamet is the main actor that plays a ping pong player. And he, to promote the movie, he went on top of the Sphere, and they made the entire Sphere like a ping pong ball. But the promo images, you can see one on the top right, they show our observatory. When they said that he's the first one to be on top of the Sphere, that's not true, because our observatory is there. We were there last summer. And it's interesting, the promo includes our observatory there. And our observatory includes both infrared cameras covering the entire sky and visible light cameras. And we have also radio receivers and audio receivers, sensors. But most recently, we were able to do triangulation, which allows us to look at a given object from different directions, and by that measure the distance to the object. So here you can see observing the same object. These are just birds, but here is the object in one image, and here it is in another. And by connecting the 2 viewing angles, using both of them, we are able to measure a distance to better than 10%. And that is something we didn't have before. It allows us to measure also velocity and acceleration, and infer whether the object is within the performance envelope of human-made technologies. This is just a video that shows the comparison of the ground truth to the inferred path of the object, and they appear to be quite close, to within a few percent most of the time. So the red is the triangulated path, and the green is the real path. And so we are constructing it in 3 dimensions. Oops. Let me oh, okay. So the next topic that I would like to focus on is the discovery of interstellar objects that was made possible only over the past decade. It's a new frontier in astronomy, an extremely important one that is not recognized by the astronomy community as such. And I will explain why it's so important. But the first interstellar object that was identified was actually in 2014. It's a meteor, and I will talk more about it. It was identified by US government satellites as a result of the fireball that it created by moving through the air. And in 2017, Oumuamua was discovered by Pan-STARRS, the Pan-STARRS telescope in Hawaii, roughly a size of a football field, about 100 meters. And it was very peculiar, as I will discuss. And then in 2019, there was a comet that was discovered by an amateur astronomer named Borisov. And then on July 1st, 2025, 3I Atlas, the third object that was identified by astronomical telescopes, was found. And by now we know that it has roughly a radius of just above a kilometer. So the size of a city, roughly. Finally, just a few weeks ago, we discovered another interstellar meteor with my postdoc. It was detected by US government satellites in 2022. Now, we can go back in time and ask each of these objects, what kind of trajectories do they follow in the gravitational potential of the Milky Way galaxy? And turns out that Oumuamua is definitely within the thin disk of the Milky Way, the thin disk of stars. That these are relatively young stars that were made out of the gas recently, whereas the older stars were kicked around by gravitational perturbations, so they occupy a thicker disk. And actually, 3I Atlas belongs to the thick disk of the Milky Way, and Borisov is sort of in between the two. Now, 3I Atlas was quite remarkable because it featured a lot of anomalies. The first one that I immediately noticed was that you can see at the bottom of this slide, it was moving within 5 degrees of the plane of the planets around the sun. And that's a chance of 1 in 500. And so why would the third object be so close to the plane of the planets? That was a bit suspicious. It's also a very bright object. I will not get into all the details. There are lots of details about it. It was observed by amateur astronomers. These are some of the images taken of it after it passed closest to the sun on October 29th. But the most unusual fact about it is that it has an anti-tail, meaning a jet pointed at the sun, whereas when we look at comets, we often see a tail, meaning the dust and gas are being pushed back away from the sun by the solar radiation and the solar wind. Whereas in this case, there seem to be a jet pointed at the sun. So potentially, this jet could be made out of relatively big particles where the solar radiation pressure is not strong enough to deflect them backwards. And moreover, as you see on the right-hand side, when the spherically symmetric coma is removed around the nucleus, one finds 3 jets that are equally spaced from each other on the sky, so about 120 degrees separating them. This is work I did with the Italian observer, Tony Scarmato. Now, recently, actually, last week, I wrote a paper that talks about the mass budget discrepancy of 3I Atlas. Basically, if you take the best estimate for the mass of 3I Atlas and multiply that by the best estimate we have for the number density of objects like 3I Atlas, if it's completely natural, it's an iceberg that came from interstellar space, you end up with a mass density of interstellar objects the size of 3I Atlas. Now, when you compare that to, the mass density of stars, and then multiply by the expected metallicity of those stars, just to find how much mass in heavy elements these stars have, because 3I Atlas is made mostly of carbon and oxygen, heavy elements. you end up with a mass density of heavy elements that is at least 10 times smaller than what you need for the population of 3I Atlas. And that's surprising. Now, the association with low metallicity stars was made as a result of 3I Atlas occupying the thick disk, but also recently based on isotope measurements. Just last week, there was a report about the detection of deuterium and carbon-12 versus carbon-13, and that indicates perhaps a low metallicity source. But as I show here, turns out that the mass density, the amount of mass in metals, heavy elements in planetary systems around low metallicity stars is actually, turns out, if you work out all the numbers, it's about at least 3 orders of magnitude, a factor of 1,000 too small than needed. So that's a puzzle. And another thing is that the mass of 3I Atlas can be calculated. In fact, this is a paper that will appear tonight on the archive. You can check it out on the AstroPH archive. Basically, I wrote down the equation of the rocket effect that you see on the top left. The rocket effect says that there is a non-gravitational force acting on 3I Atlas, which is the mass times the acceleration. Okay, that's the force. And that is equal to the rate by which mass is lost in a preferred direction. So if mass is lost in some direction and it carries a certain velocity, so then there is momentum lost in that direction, and the time derivative of the momentum gives you the force, and there is momentum conservation. So that's the way that a jet airplane works or a rocket works. That's the rocket equation, and it should apply to 3I Atlas. So we can calculate the mass of this object by measuring the non-gravitational acceleration that it has and the mass loss rate that it displays. And of course, the velocity of the gas can be estimated from the sound speed of the molecules that we observe. And so when you do that calculation, based on all the data that was collected about 3I Atlas with the Webb telescope, with the Hubble telescope, you end up with a mass that is about 10 to the power 12 kilograms, or a mass that is about 1 billion tons, metric tons. And this mass is a factor of 100,000 bigger than the first interstellar object, Oumuamua. Now, when we look at objects in the solar system, we usually find equal amount of mass per logarithmic mass interval. And this means that we should have seen 100,000 objects as small as Oumuamua before we see one big object as big as 3I Atlas. But instead, we saw one object like Oumuamua, then there was Borisov, and now we have 3I Atlas. So what's going on here? That's a huge discrepancy. Why haven't we seen 100,000 small objects before seeing one giant object? That makes very little sense. And perhaps one or both of these mysterious objects is not natural in origin. Now, I actually, I write, as I said, I write on medium.com, and in one of my essays, recently, last week, I summarized all the anomalies about 3I Atlas, and there are 22 of them, 22 anomalies, things that are not in line with what we expect, similar to the mass budget discrepancy that I mentioned, and now also the jets, the mini jets, and so forth. So there are geometric anomalies, like why is it in the plane of the planets around the sun? Why is there a symmetric set of jets, and all kinds of other? You can check my list. And there are also alignments. For example, 3I Atlas was in the direction of the WOW signal from 1977 to within less than 1% chance of that coincidence. Also it showed evidence for biological signatures, like organic molecules that are used as biomarkers, like methane and carbon dioxide and CO, carbon monoxide, and so forth. So there are lots of anomalies, and nevertheless, these are being ignored. They are not being discussed. Just to give you an example, there was a detection of a nickel with very little iron back in July and August last year. And the only place where we find nickel with very little iron is in industrial production of nickel alloys. And it's called the carbonyl chemical pathway. So what did the authors of the paper do? What they said is, oh, maybe nature is employing this industrial production pathway. Maybe nature has the carbonyl pathway to produce nickel with very little iron. Instead of saying, wait a minute, is that a technological signature? Because we use this process for aerospace applications. So these are some images of 3I Atlas in different types of molecules, but including organic molecules. And the interesting question is whether there is any life form on 3I Atlas, because if we wanted to seed the Milky Way galaxy with life, we would not put microbes on Voyager. We would put them in a capsule that collides with 3I Atlas and plants some microbial life inside of it, so that when it gets to another star and evaporates, it will release those, and we would seed another star with the kind of life as we know it. That's a much better way, because 3I Atlas is moving at 60 kilometers per second, at least twice as fast as all the rockets that we ever launched. Just to give you an example, a couple of months ago, it came close to two spacecraft that are on their way to Jupiter. One is the Europa Clipper, and the other one is JUICE. So it came close to them a couple of months ago, and now it's actually arriving today to Jupiter, today. And these two spacecraft that are human-made will arrive only in 2030 and 2031 to Jupiter. So if you wanted to get to hitchhike to interstellar space, it's much better to use such an object. And the other comment I will make is that if we were smart enough, we would intercept 3I Atlas and bring materials from it back to Earth, because that would allow us to check for the building blocks of life as we know it, if they exist around another star. Instead of investing $10 billion in observing remotely far away planets, or actually it's completely impractical to visit other stars and report back with current technologies. It would take millions to billions of years. But here is an object that came from another star. We could just scoop it, bring material back to Earth, and learn whether there are building blocks of life in it. And even if it's a natural rock, that would be of great importance, and nobody talks about it. And the system of jets that are near the nucleus is actually wobbling. We measured it, and it has perhaps associated with a rotation period of about 7 hours of 3I Atlas. And the amazing thing is the rotation axis is directed at the sun, roughly, to within 10 degrees or so. Now, back in July, when this object was identified, I suggested the classification scale. It's now called the Loeb scale classification, and 0 on that scale means an object that is definitely natural, an asteroid or a comet from another star that poses no threat to humanity. And 10 means an object that is alien technology, that is a significant potential threat to humanity. And this is important in order to help policymakers to decide how to respond. We don't often talk about potential risks to humanity from a supernova that happens at gigaparsecs away. It doesn't have any impact on Earth. So we are used in academia not to be relevant to policymakers if we are astrophysicists or cosmologists. But it's interesting that when I suggested that and didn't expect much attention from governments, but then someone sent an inquiry to the CIA, the Central Intelligence Agency in the United States, whether they have any records related to 3I Atlas. And what they said is, that they can neither confirm nor deny the existence of records on 3I Atlas. If they didn't have, they would simply say, we don't have anything. So that means they had some discussions about it, perhaps related to my paper on the classification scale. And then also at the end of 2025, on December 19th, when 3I Atlas came closest to Earth, there was a summary of 2025 held in Moscow, in Russia, and the Russian president, Vladimir Putin, was asked by a journalist about what did he learn from his intelligence agencies about 3I Atlas. So this is the exchange that you see here, and the journalist asked, could it be alien technology? And Putin responded that yes, he was informed about this object by his intelligence agencies, and he believes that it's most likely a comet. That's what the scientists are telling him. So it's really interesting that governments around the world, I think this is the first astrophysical object that governments are talking about in real time. And I had correspondence with Congresswoman Anna Paulina Luna, and told her that it would be very helpful if the Juno spacecraft would observe 3I Atlas, actually today, when it's coming close to Jupiter. And she wrote a letter to NASA encouraging them to do that very graciously. So let me say a few words about the first interstellar object, Oumuamua. It was anomalous in different ways than 3I Atlas, because basically it was roughly the size of a football field, and as it was tumbling every 8 hours, the amount of sunlight reflected from it, its brightness, changed by a factor of 10. And that's very unusual. It means that the area projected on the sky was changing by a factor of 10. So it means the object has a very extreme shape, and most likely flat, based on the analysis of the variation in reflected sunlight. So you have a flat object that is very thin in order for the amount of the area projected on the sky to change by a factor of 10. Moreover, it showed an excess push away from the sun, a non-gravitational acceleration, but there was no gas or dust detected around it. The Spitzer Space Telescope looked very deeply, couldn't find anything. So I suggested, since the acceleration was declining inversely with distance squared, I said, well, maybe it's the light from the sun that is pushing it. For that, the object had to be very thin, like a sail, or like a fragment, a broken piece of a Dyson sphere, or something technological. And that became that was published in the Astrophysical Journal Letters, and then immediately got a lot of attention, and many people within the scientific community expressed their hate to this possibility. And I find that really strange, because in principle, if we had enough data, we could tell the difference between a light sail and a rock. And right now, the comet experts insist that it's a dark comet, meaning a comet where you don't see the cometary tail. And I feel like the kid in Hans Christian Andersen's tale that said, the emperor has no clothes. And the adults in the room were saying, oh, no, the emperor has clothes, you just can't see them. And this is the dogma within the mainstream. So the dogmatists are saying there are things that you can't see. And I say, what we see is what we get. So who is more reasonable? And I should say also that on January 2nd, 2025, the Minor Planet Center that catalogs near-Earth objects announced a new asteroid, and a near-Earth asteroid. And then a day later, they realized, oh, wait a minute, this asteroid is actually moving along the path of the Tesla Roadster car that was launched by SpaceX in 2018. So it's not a rock, it's a car. So they took it out of their catalog. But imagine another space entrepreneur, better than Elon Musk, that launched a car to interstellar space. When they would see it, they would not know the path of this car because we didn't launch it. So they would say it's a rock of a type that we've never seen before. Should we believe them? By the way, if a cave dweller would find a cell phone, the cave dweller would say, it's a rock of a type that I've never seen before, because the cave dweller is used to playing with rocks. And comet experts were basically trained on a data set that includes only rocks, just like LLM or AI systems. And I say, you should expand your training data set to include technological objects, and then allow your imagination to play a role in the way you interpret things. In fact, the same telescope in Hawaii, Pan-STARRS, discovered another object after Oumuamua that was pushed away from the sun by reflecting sunlight. Then they measured the spectrum and found that it's made of stainless steel. Turns out that it was a rocket booster that was launched in 1966 by NASA. So we know that we produced it, and therefore it's technological. But who produced Oumuamua? And by the way, some people say, oh, it's a very large distance that separates stars in the Milky Way galaxy. Do we need wormholes? Do we need faster than light propagation? No, even with our 1970s technologies, Voyager, the Voyager spacecraft, we integrated the orbit of the Voyager spacecraft in the Milky Way galaxy. Within 1 billion years, it will be on the opposite side relative to the sun. Voyager from 1970s technologies will make it in a time scale that is shorter than the age difference between the sun and most of the stars in the Milky Way galaxy. Most of the stars in the Milky Way galaxy are billions of years older than the sun. There was plenty of time for Voyagers to reach our backyard from civilizations on the opposite side of the Milky Way galaxy. You don't need faster than light propagation, because Voyager is propagating at a speed that is 10,000 times smaller than the speed of light. That's enough. Now, just a few weeks ago, we posted a paper with my postdoc that reports about a new interstellar meteor that basically an object that collided with Earth at a speed that exceeds the escape speed from the solar system. And my hope is to go and visit it, because the first interstellar meteor from 2014 triggered my interest in leading an expedition to retrieve materials from the site of the fireball that was created as a result of its friction on air. And the US government, the US Space Command, released data on the flares, 3 flares that came from this fireball, and they provided the information about the location. And so I decided to lead an expedition there. It cost about $1.5 million. It was done in June 2023. And basically what we used is a sled that you see in the middle panel, the top panel, a sled covered with magnets that we placed on the ocean floor at a depth of 2 kilometers, and then collected materials by going back and forth across a region of 10 kilometers in size. We went 26 times back and forth and collected materials from the site of this meteor. And I brought the material back to the laboratory of my colleague at Harvard, Stein Jacobson. Here you see us on a rainy night searching for the material on the magnets of the sled. And this is an image of Stein Jacobson on the right-hand side here, who has the best equipment in the world for analysis of the composition of the material we brought back. And on my other side is Sophie Bergstrom, who found most of the molten droplets in the sample that we brought back, 850 spherules that looked very distinct relative to the background sand. You can see here the background sand, and this is one of those molten droplets, a spherule. And there were different types. We found that 10% of the fragments that we brought back have an unusual composition, chemical composition. So you see here elements from the periodic table, starting on the left. They're organized by compatibility. That's a term that is related to chemical geology. On the left, on the left, you see uranium and then beryllium and so forth. These are the elements. And the vertical axis shows the abundance of these elements relative to the standard solar composition of the materials that made the solar system. And some of the elements have up to 1,000 times higher abundance in this sample of spherules relative to the standard composition of solar system materials. So we suggested maybe that's good evidence that they came from outside the solar system. And other people said, oh, well, maybe it's coal ash. So we compared it to coal ash. It's nothing like it. Then they said, maybe it's tektites. And we compared it to tektites. It's nothing like it. This is a very unusual composition that we gave it a name, belau, because beryllium, lanthanum, uranium are of a very unusual abundance in this sample. And I should say also something that is not displayed here yet, but we just discovered new evidence that is beyond any doubt, that is not based on chemical composition, but based on isotope abundances. We measure isotopes that demonstrate that it's definitely from outside the solar system, because it's very difficult to change the relative abundances of isotopes by processes on planets, asteroids, comets. You really need the nuclear reactions to change the number of neutrons within an atomic nucleus, or you need the bombardment by energetic particles. That doesn't happen in planetary systems. And we found the isotopic composition that is very unusual and different from solar system composition. So we have very clear evidence. This is a work in preparation, a paper in preparation, clear evidence that we identified materials from outside the solar system. And of course, it could be of natural origin. For example, the most common type of stars are dwarf stars. And if you have a rocky planet that comes close to a dwarf star, it will be tidally disrupted because a dwarf star has a mean density that is 100 times the mean density of the sun. A dwarf star that is 1/10 of the mass of the sun has roughly 1/10 of the size of the sun. So the density is 100 times bigger, because the density is the mass divided by the volume, which goes like the size cubed. So it turns out that if you take the Earth, sorry?
Loeb, it's a humble request if you can conclude.
Yeah, I'm about to conclude.
Yeah, okay.
So if you bring a rock close, the Earth close to the sun, it will not be disrupted. But if you bring it close to a dwarf star, it will, and you will end up with some material ejected to interstellar space in this process. What we hope to do is collect bigger pieces of this material to figure out the nature of this object. And also, of course, a very important observatory is the Rubin Observatory in Chile that will find many more interstellar objects. It employs a camera with 3.2 gigapixels. The data is already coming in. And finally, I would like to point out that we have the Rubin Observatory in the south, looking at the southern sky, but there is also a plan for the Argus Array Observatory that will monitor the northern sky. That will allow us a full sky search, and there should be dozens of new interstellar objects in the coming decade that we find. And it would make sense to build an optical interferometer on the moon with more than 100 meters baseline that can resolve objects like 3I Atlas at a distance of roughly 1 astronomical unit, the Earth-Sun separation. And finally, we need to have interception missions that will take a close-up photograph or potentially protect the Earth. As I mentioned before, if we were to collect materials from these objects, bring them back to Earth, we could actually learn much more about life in the Milky Way galaxy in a way that is very different than the Habitable World Observatory that is currently being planned for remote observing. Thank you very much, and I'll be glad to answer any questions.
Yeah, thank you, Professor, for your brilliant talk. And I would like to express my sincere gratitude to you for sharing such profound results and enriching us with your work on interstellar objects. So thank you. So a gentle reminder to the audience that you may continue submitting your questions by scanning the QR code displayed on the screen. So we have got many interesting questions, Professor. So question, please. So yeah, this is a question by Professor Tejendra Singh. It's from Tata Institute of Fundamental Research, Mumbai. So he's asking that in early 2025, a group of about 30 scientists published a 200-page article on Archive titled "The New Science of Unidentified Aerospace Undersea Phenomena." Does this article provide credible evidence for the non-human intelligence in the Earth's environment? If not, then how to understand what UAP are?
Well, that's an excellent question. All the data that was released so far or reported is not of high scientific quality. We cannot use it to argue that it's beyond a reasonable doubt that we are being visited by technological artifacts from outside of this Earth. Now, it's possible the US government has such data, but that's classified, and that was the purpose of President Trump's directive to the Pentagon and the intelligence agencies. And of course, if they have such materials or such data, I would love to help them figure it out, but it wasn't released publicly. So that, again, I say, keep your eyes on the ball, okay? So the fact that the archive posts a paper is irrelevant. The question is, keep your eyes on the ball. What is the evidence? Is there evidence? And of course, if there was evidence that is beyond any doubt, we would all know about it. So the fact that there was an article, the fact that there were 30 people signed on it is completely irrelevant. You should never believe stories that people tell you. You should look at the evidence. And, there were 100 people that wrote a book when Albert Einstein, after he came up with his theory of relativity. So a decade later, they wrote a book saying why relativity is wrong. 100 authors against Albert Einstein. And so when a reporter asked Albert Einstein, what does he have to say? He said, you don't need 100 authors. It's sufficient to have one as long as they make a clear argument that is indisputable. So you don't need 30 scientists on an archive preprint. What you need is a kid that shows you a photograph of a technological object or materials. It's enough to have one person, but the evidence is the key, not the number of people. People are completely irrelevant.
Yeah, well, thank you, sir, for your thoughtful response. So another question, please. So it is questioned by Louis Marmot from York University. So it is quite trivial that other life form must exist elsewhere in the universe. However, as signals and matter decay while traveling through space, communication between life forms across intergalactic distance is improbable. The cosmic time scale involved are also much larger than the lifetime of civilizations. How is observing alien not an extraordinary claim?
Okay, so let me explain. I don't know if Louise that asked this question has kids. But if you have kids, I have 2 daughters, when they leave home at a later age, you don't expect them to report back and tell you about each and everything that happens to them. It takes a lot of time. And in fact, they may be far away. What you expect is them to operate independently based on the guiding principles that you educated them about. And so when we send, for example, a spacecraft to an interstellar mission, we should not expect it to report back. The only missions that we launched so far to the moon or other planets in the solar system, it's such a close distance to us that, we are sort of like we are helicopter parenting these instruments. Helicopter parenting is a description of parents who really want to know everything about their kids and keep looking at them over their shoulders. So the engineers in the Jet Propulsion Lab at Pasadena are helicopter parenting all the gadgets that were put on Mars, all the robots, all the rovers. But that's possible just because Mars is so close to us. When you send something outside of the solar system, you can't helicopter parent that. You have to put some artificial intelligence into it so that it will make its own decisions, just like your kids when they leave home. And you have to trust that it will fulfill its mission. So the fact that it doesn't report back, it doesn't really mean that you didn't send them. I sent my girls out of my home. I know that they are out there. And the fact that they don't communicate back everything that happens to them doesn't mean that I didn't send them. So in the same vein, you can send, if you have a goal, for example, to seed the Milky Way galaxy with those technological gadgets, you will send them out, let them do their thing. You might even send self-replicating probes that can multiply exponentially in number by using raw materials from the sites that they visit. But the fact that they cannot communicate in real time to the senders doesn't mean anything. It doesn't, you know, when the dandelion flower is a flower that sheds seeds, and nature already arrived at this solution. The dandelion sheds seeds. It has no umbilical cord that connects the flower to the seed. The seed is sent and carried with the wind and lands on a fertile ground. And then the DNA of the dandelion flower lets a new flower come out. But there is no communication back to the original flower. So nature already thought about your question. And the solution is you just send out your seeds and let them do their thing. You don't need to connect them to you with an umbilical cord of some means of communication.
Yeah. Yeah, thank you, Professor, for this answer. So this is question by Dr. Bharat Pandey, Government PG College, Ranikhet, Uttarakhand. Sir, I want to ask that if scientists ever find an unusual object near Earth or in our solar system, how will they know whether it is a natural space object like an asteroid or something artificial that might have been made by advanced extraterrestrial civilization?
Yeah, that's an excellent question, and I discuss it in many of my essays. So the simplest way is to have a close-up photograph, because then you can tell the difference between a rock and the technological gadget. For example, the gadget may have buttons on it. And then the question would be, should we press a button? Or you would see some technologies that we cannot produce ourselves, you know. So it's basically the more data we have, the better. You know, I'm extremely happy with a flood of data. If we could get as much data as possible. Now, what happens with dogmatists in science? They don't want new data. They know the answer in advance. They say it's an extraordinary claim. Let's not invest anything in looking for data. And my point is that preserves our ignorance. I would love to get as much data as possible. That's the way that science makes progress. Because once you have a lot of data on an object, it will not be possible to shove the anomalies under the carpet of traditional thinking. So if we have a high-resolution image, or we have access to the materials of the object, we should be able to easily tell whether it came from outside the solar system. As I told you, with isotope abundance measurements, we are doing that for the interstellar meteor from 2014 right now. And obviously, if there is a big piece that looks technological, you can immediately say that. So there are simple ways to tell the difference between a technological object and a natural object, as long as we have access to high quality data.
Yeah, thank you, sir. Thank you very much. So we have next question by Vedant, IIT Kharagpur. It's asking, do you think we should look for extraterrestrial life in the solar system itself? Because it is difficult to discover such a thing without actually visiting or sending a probe or rover to that celestial body. If yes, then what are the possible candidates? Is Titan one among them?
Yeah, so I guess the question is asking about microbial life or primitive life, and it's very likely that it existed on Mars, because early on, Mars had very similar conditions to those on Earth. We can see the evidence that the early Mars in the first 2 to 3 billion years, half of its current lifespan, Mars had liquid oceans, rivers, lakes, just like Earth, and it had an atmosphere, so the conditions were ripe for it to have life as we know it. In fact, Mars cooled before Earth because it's a smaller body. It has more surface area for its mass, per unit mass, than Earth. And so it may have reached the conditions for life before Earth, and there were rocks that were exchanged between Mars and Earth, and it could have been that life emerged on Earth after a rock from Mars brought it to Earth, in which case we are all Martians. And when Elon Musk wants to go back to Mars, it's just like a kid wanting to go back to their childhood home. So Mars is a good place to look for it. Unfortunately, NASA became extremely cautious at pursuing evidence for microbes. For example, they send rovers and probes, but they don't do the obvious thing. They don't take a piece of soil and put a drop of water in it to see if anything comes out, any gases indicating life. And so it's really unfortunate because there was some early evidence from the 1970s that perhaps there is life, evidence for life on Mars. But then, of course, there are Enceladus and Europa that have plumes of water vapor coming out of the cracks in the ice, and it's clear that there is a liquid ocean, water ocean under the ice, and it could have life. And then there is Titan, which is the only other body in the solar system that has liquids on its surface aside from Earth, except Titan is at a temperature of 91 degrees Kelvin. And the liquid on the surface is not water, it's methane and ethane. And so if I had my wish, I would actually like to go fishing on Titan to see if there are any fish in these liquids. Life as we know it is in liquid water, but maybe other liquids support life as well.
Yeah, thank you, sir. So another question, please. So this is questions by Dr. Ravi Sharma, recipient of NASA Apollo Achievement Award, and he's was a former scientific secretary ISRO headquarters. So he's asking, I used SAU and Broker Nunn and NORAD during Apollo, and we funded SAO from NASA HQ quarters to track objects and dump from Apollo. How much more the SETI and SAO networks have increased for near Earth objects, that is our solar system? How do we identify for sure that they are extrasolar origin beyond Oort clouds?
Yes, that's an excellent question. First, I should say that SETI is not the community that I operate from within, because the SETI community was engaged with a search for radio signals over the past 65 years. And they are very much opposed to the research on objects near Earth as a possible technological signature. They banned any discussion on this subject in their conferences, which is very surprising, by the way. However, speaking about the subject that you brought up, I should show, I wrote an essay just a week ago. Let me share my screen so you can see it. It's about an object that was found by the Curiosity rover, an image that the Curiosity rover took of Mars. Let me just show it to you. 1 second, I'll find it. It's really, it became viral, you know, this image just last week. So let me share my screen. You can see it. You can see it here. So this is the essay that I wrote on Medium, you know, that's on March 7th. And I basically talk about this image that you see here that was taken of some, you know, place on Mars. And you see all these rocks, but then here, look what's popping out from the regolith on Mars. It's a cylindrical object that definitely looks artificial. Where is it from? Is this a piece of material that, you know, is associated with a Curiosity rover or another human-made rover that or spacecraft that passed above this place? But it's very peculiar. This is definitely real because you see this cylinder, which is roughly 20 centimeters in length, sticking out. You can see it from different angles from the camera on the Curiosity rover. Now you would think, oh, NASA should make a comment about it. But no, they're not willing to say anything. They don't say anything. They never noticed this. After this was noticed, they don't make a statement about it. And right now, the Curiosity rover is about 8 kilometers away from this site. but given its maximum speed of 160 meters per second, it could go back within a matter of a few days. And I think it's a high priority. Why not find what this thing is? After all, the name of this rover is Curiosity. That's the name of the rover, and NASA doesn't show any curiosity. So anyway, that's just to address your question about, finding technological relics in various missions. And of course, there are also a lot of technological debris in space that is human-made, that is often mistaken for natural objects. But we should be able to tell the difference if we find anything that is extraterrestrial.
Yeah, thank you very much, sir, for this brilliant answer. So we are already up to the time, but we have 2-3 questions more. So should we extend it or?
Yeah, you can ask quickly, and
Sure.
I'll answer. Yeah.
So this is question you're asking that when we search for aliens or higher intelligence out there, we generally assume that they should also have carbon-based bodies like us. What if aliens' bodies are not carbon-based?
Oh, it's quite possible that they're not carbon-based because, for example, we are now transitioning to a future where artificial intelligence is really dominating the scene, and artificial intelligence systems are made of silicon, right? The silicon chips. And by the way, we tend to think of AI as if, we can train those AI systems and align them with our principles so they would look like us. But the way I think about it is like if you have a pig, you're trying to put lipstick on the pig so that it looks more beautiful. It doesn't make the pig human. So for the same reason, training AI will not make AI systems like humans. They are something different. They are alien intelligence. And, in the future, we will be potentially dominated by the way AI affects us. And in principle, we could supplement our body with all kinds of gadgets that are not biological, perhaps extend human life well beyond what it is now. Maybe we will live forever, so you can send astronauts for very long trips. So if we meet someone that represents our future, it may not be biological. It may be AI. It may have an AI brain and may have a body made of silicon. I don't know what, but I don't want to imagine. I just want to observe it.
Yeah, thank you, sir. So it could be the last question. The question is by Roy, Asutosh College, Kolkata. He's asking, however much it has been branded as a pseudoscience, the extraterrestrial phenomena, their frequency, their appearance throughout the history of Earth, which is well recorded. Also mathematically, the drag equation and anomalies we have observed throughout Earth do point to a consistent result. What do you think is the most significant proof that needs much more analysis or research?
Yeah, so again, it's an excellent question. And the problem with this field of study is that there is a lot of nonsense being said. A lot of misinformation. People come up with stories that make no scientific sense. There is a lot of noise. And that's why many scientists prefer not to work on this subject, because they say, oh, we will be flooded with nonsense that people say. That's not a good enough reason, because nonsense was said throughout human history about things that are now part of science, including medical science. There was lots of nonsense. What we should do is focus on the scientific method, which is based on what we already know, which is the laws of physics. Many science fiction writers and other people say, oh, there could be new physics. Well, it's very difficult to come by new physics. It's not easy. You just heard a talk by Wendy Freedman where people debate for years about whether there is new physics or not with the Hubble tension. It's a lot of work. You can't just say, I imagine moving faster than light. I imagine, that's possible for a science fiction writer, but not in science. The laws of physics are not easy to come by and change, and so we should accept what we already know within physics, and then be open-minded to anomalies that will inform us. But the way we learn about new knowledge is through experiments, through observations. and not by storytelling. And so there is a lot of storytelling, a lot of misinformation, about a lot of nonsense being said about this subject. And my solution to that is to ignore all of that and focus on the scientific method, because this is the most consequential question that science can offer to society. Are we alone? That's the most consequential. It will change the future of politics. If we find a neighbor, we would realize that we should behave differently in the future. Just like when someone knocks on the door of your home, suddenly, if there was a loud argument within your family, people stop arguing because they don't want to leave a bad impression on the visitor. You know, so when we realize there is someone visiting us, we will change priorities. Right now, if you look at the newspaper, we are always engaged in conflicts around the world, but it will change our perspective and what we wish to do in the future and our aspirations for going to space and how to protect the Earth and so forth. We would feel part of, you know, the same species. We are all members of the human species. We are all in the same boat, and so we should work together. I see it as a path that is full of optimism, that will bring humanity to a better place. And that's why I pursue it, despite all the resistance that I get within the scientific community. I think it's the most important subject that should be funded at a level of billions of dollars so that we can make progress.
Yeah, thank you. Thank you very much, sir, for answering this question with profound clarity and depth. And on behalf of Bhaktivedanta Institute, I would like to thank you for sharing with us your insights and wisdom. And it has really changed. I hope it may have changed the perspective of many of us. So thank you very much, Professor Loeb. Thank you.
Thanks for having me. It's a great pleasure to join you. And I hope someone listening will help to make the revolution, the next scientific Copernican revolution.
Yeah, I hope so. Thank you, sir. Bye.
Bye-bye.
So, So tomorrow we have lined up a world-renowned speakers, and we warmly invite all of you to continue joining us to these fascinating sessions. So as you can see, it is a schedule for tomorrow's sessions. So we will start our sessions tomorrow at 5 p.m. And we have the first talk by Professor Paul J. Steinhardt from Princeton University. He is one of the leading cosmologists of our time. And Professor Steinhardt has made groundbreaking contributions to our understanding of the early universe, including revolutionary ideas such as cyclic cosmology. So in his talk, Time to Take the Big Bang Out of Big Bang Theory, he will challenge some of the deepest assumptions about the origin of the universe. Next talk will be starting at 6 p.m. and Professor Pankaj Joshi from International Center for Space and Cosmology, Ahmedabad, will deliver his talk. And Professor Joshi has devoted decades to study this gravitational collapse and black holes. So in his lecture, The Story of Black Hole, Life and Death of Massive Stars in the Universe, he will share insights from his pioneering research into one of the most mysterious phenomena in astrophysics. So the third talk will be by Professor Andrew Linde of Stanford University, one of the architects of modern interplanetary cosmology. And his ideas have profoundly shaped our understanding of the early universe and the concepts of the multiverse. So in his talk, Universe and Multiverse, Professor Linde will explore one of the most exciting and profound questions in modern cosmology. So please join us tomorrow for this inspiring lecture from some of the greatest minds in cosmology. So we look forward to your continued participations. So there are a few publications from Bhaktivedanta Institute. The first is Quantum Physics and Consciousness. So this is a very beautiful volume which offers a very rare and intimate glimpses into the foundational thoughts of the founders of quantum physics, including Max Planck, Niels Bohr, Werner Heisenberg. And this collection focuses on the fascinating moment in history when the discovery of quantum mechanics began to reshape our understanding of the physical world. exploring how these Nobel laureates, for example, Eugen Wigner, Anthony Leggett, navigated the profound scientific implications of their own revolutionary research. So you are welcome to discover more about this by visiting our online collection at store.biinstitute.org. And the second very beautiful magazine, Tattu Jigyasa, it's a magazine from Bhaktivedanta Institute that examines foundational questions at the intersection of physics, cosmology, and other areas. And this volume brings together a contribution from distinguished scholars exploring scientific perspective on the nature of universe and its underlying principles. So this is especially Tattva Jigyasa Volume 2 features insightful dialogue between Dr. Robert Ma, Senior Research Scientist at NASA, and Dr. T.D. Singh, Founder Director of Bhaktivedanta Institute, where they discusses perspective on space exploration and the broader scientific implication of studying the cosmos. It also includes an thought-provoking article by Dr. Bernard Hayes, astrophysicist from University of California, examining cosmological questions concerning the structure, origin, and underlying order of the universe. So again, we warmly invite you to explore these articles by visiting our store.biinstitute.org. So once again, I would like to remind you about the timings of the lecture, which will start by 5 p.m. and end at 8 p.m. from Monday to Friday. And on the weekends, Saturday and Sunday, the lecture will start at 10 a.m. to 1 p.m. in Indian Standard Time. So once again, I would like to express my gratitude to all our speakers, dignitaries, guests, and all our participants for joining us today. Thank you all, and hope to see you all tomorrow. Vice-Chancellor, ये टाइप है